Are you guys ready?
Yeah.
You're in.
Okay.
Alright. 20 to 30 years from now, order your package from Amazon, you're like, want it in less than 30 minutes. And it comes to you in less than 30 minutes. How does it do that? Well, we think it's going to go through this complex, low altitude, high density airspace, and your package gets onto an unmanned aerial vehicle, a UAV, and it's delivered straight from the storage warehouse directly to your house. Now, this might seem all simple and fun, but when you think about the current reality, this is what we're dealing with right now. Currently, UAV to aircraft and UAV on infrastructure collisions are very common, as you can see. As autonomous UAV operations become much more prevalent, UAV on UAV collisions will also increase in frequency. And that's the domain, that's the problem domain that our senior design project wants to tackle. So because of these various safety issues, the FAA has become very conservative in terms of relaxing safety standards and regulation for autonomous UAV operations. In fact, sometimes they straight out ban them unless you get a waiver ahead of time. But in spite of these restrictions, UAV tech continues to proliferate. Companies individually are trying to get on this bandwagon, and they're seeking individual waivers and exceptions to FAA's rules. And furthermore, even for us, the general population, UAV technology becomes cheaper and more accessible by the day. But note that there is currently a lack of a coordinated technological framework to kind of get all these people and parties who are interested in UAV together. Now, that's exactly where we find ourselves. Our product hopes to help bridge one of the technological gaps that we have identified. And we first take inspiration from the commercial air traffic control system, in that we leverage a centralized approach in dealing with UAV on UAV traffic management. So instead of the pairwise approach where you have sensor, where you would require a lot more sensing capabilities and also computational capabilities, using a centralized approach kind of get rid of that kind of burden. Furthermore, our system is versatile and scalable. You can implement it on any UAV platform, and you can scale it to the city of your size. It can also handle whatever amount of UAVs you throw at it. Our system is very interdisciplinary and complex, but you can kind of break it up into these three main components. The hardware and embedded systems part, the software component, and then finally the systems testing and systems compliance. So now I'll turn it over to Sahithya, who will go over more of the hardware and embedded system aspect.
Thank you, Max. So one of the major challenges our team had to overcome was being able to manually fly the UAV. In order to do this, we had to assemble the UAV, attach propellers and motors, and add the PIXHawk flight management unit. The PIXHawk is responsible for sending commands to the motors based on the information it receives from the onboard sensors. The onboard sensors that we included are the GPS, LiDAR, compass, and any other components that enable communication between the UAV and the ground station and the joystick controller. This is a picture showing the two UAVs we built from scratch. Both of them have the onboard sensors mentioned previously, as well as the O-Droid, which is the onboard computer that communicates with the PIXHawk. Specifically, the O-Droid sends commands that change the UAV's mode, velocity, or position. It also receives vehicle status and data from the PIXHawk. So once the UAV approaches an intersection, the PIXHawk sends its mission to the O-Droid, which then relays that mission to the reservation system. Based on the response the O-Droid gets from the reservation system, it will send a command to the PIXHawk, either telling it to hold for X amount of seconds because it found a collision, or continue on its mission. This is a picture showing the O-Droid on the UAV. The O-Droid is connected, the O-Droid communicates with the PIXHawk through the MapLink protocol through the USB UART interface. The GPS, LiDAR, and compass are the main sensors that update the UAV status, and the O-Droid uses this information to detect errors such as GPS glitches. I will now turn it over to Jack, who will talk more about the software and reservation system.
So the UAV first communicates with our relay server, part of our software system. So the relay server has the responsibility of handling all the incoming requests from UAVs who are trying to preserve a path through our airspace. In each of these requests, the UAV sets its waypoints, which can be thought of as the main points that characterize its mission. So each of these waypoints are sent back to the reservation system from the relay server. So the reservation system, the relay server, and the UAV are all in different frames of reference. So we need to go through a couple of processes of different coordinate transformations and different other processes to get them all on the same page. So looking further in, we take the spline of the waypoint path and compute a region of bounded uncertainty. So then we eventually end up mapping this onto our voxel reservation system grid. And then this path is then passed along to check if the reservation is valid or not. And it does this by comparing against previous reservations that have already been made in order to detect any possible future conflict. So then this result is then passed back to the UAV as a hold or clear status.
So I'm going to talk a little bit about the hardware and software testing that we did, the engineering standards that we had to abide by, as well as the ethical considerations that we explored. So this is a picture of the PerchNet at the Pennovation Work Center. Due to the autonomous nature of our project, we had to do all of our in-flight testing within this net because it's an enclosed area. So this is our technical setup when we were testing. We did a lot of the software testing using offline simulations, varying the different parameters for the traffic. This is a similar setup that you'll see at the demo here as well. So we also had to abide by some of the standards and regulations. So the FAA's most prominent standard that you had to abide by was 14 CFR Part 107, which outlines the different restrictions for altitude, speed, and line of sight, and we complied with these by flying within the PerchNet. We also abided by the FCC standard, personal radio services, by having all our RC units transmit through an acceptable bandwidth. Our system is using a first in, first out queue, so there's no bias, so therefore we're abiding by the IEEE's algorithmic bias standard. So we've complied with all the standards regarding autonomous UAVs. However, there are not that many in place right now, so we're hoping that our project serves as a technological framework to provide new legislation in the future that will lead to the mass adoption and use of autonomous drones. However, before this can take place, there are a lot of ethical issues, such as security, privacy, and loss link scenarios that need to be addressed before this can happen. So to conclude, our project is essentially an essential first step in the process of bringing in the UAV to the mass markets. So thank you for coming to our presentation, and we hope that you come to our This is Austin, Marcus, I'm Colin Leslie. Thank you for your time. Creativity is hard to replicate, but easy to inspire. This has been proven throughout humans past, like with events, like an apple falling on Isaac Newton's head, or water in the bathtub rising as Archimedes enters. So one has to wonder, if something as simple as an apple or water can inspire such brilliance, shouldn't a computer be able to do it better? Our senior design was dedicated to explore this question. So the next question was, what field should we use? Because we wanted one that shows the power of a computer, but also is the epitome of human creativity. And we decided music theory is the best. So the problem we decided to solve was, when creating music, composers are faced with many pain points, but specifically, the biggest pain point that they have to face is the creation of a unique melody. And it's one of the main reasons in surveys why amateur composers decide to stop, because they get frustrated from this pain point. So we decided that we wanted to create a creativity assistant for the composer to prove the capability that computers could inspire creativity, and that it had to be tailored to the individual's needs and create short seeds of melody to help with composition. This sounds all great in theory, but what exactly did we want at the beginning of the presentation, or at the beginning of the project, rather? Well, we knew we wanted to create a web-based application because it needed to be accessible to any users, even the amateur composers that don't necessarily have money or access to software. And we wanted to efficiently generate unique melodies, eventually being able to bring it down to less than 1/4 of a second per melody generation. And we wanted to also dynamically tailor our presentation of the melody to what the user specifically wants to hear, so the specific composer can enjoy hearing the melody that they're producing and enjoy their work in general, so that they're inspired to continue further. So they input tempo, chord progression, other inputs, but then we wanted to also output it as a MIDI file so that it can actually interact with the tools that classic composers use, like keyboards and other MIDI devices. And then we also derived rules for melody generation through the application using machine learning, observing existing music. Marcus will talk further about the design of the product.
So here's a flow chart for the design of our software. First, as Colin said, we parse MIDI streams available online in order to apply machine learning to those outputs and create a melodic database. From there, we can combine it with the user input in order to create the melody tailored to our users' needs. Then we push that through multiple open source APIs that can translate that into a MIDI file. And we add rhythm generation and chordal accompaniment that we work on separately from that model. And then once we do all that, it comes out as a MIDI output and memory, which we can push to the front end for the user to listen to or download and use for his other software for composers.
Key ideas of this are that we use Markov modeling and stochastic rhythm generation independently and then combine them together.
To talk briefly about the core model now, working music operates under this core assumption that we can always probabilistically choose the next note in melody, under the assumption or given that we know the distance between the previous and the current note. To explain what distance means, within a scale there's 7 notes. We can assign an index 0 through 6 to each note within the scale. The distance between notes then is the difference between indices of the notes in the scale. If you look on the left, you see a probability transition matrix. That's for the pop genre. The x-axis gives the distance between the previous and the current note. Given that we know that, you can select then a vertical column out of the matrix, giving a probability distribution function on the distance between the current and the next note. We believe we've generated a valuable model of music. In generating this model, we selected roughly 100 representative songs from the pop and classical genres, therefore generating clinician matrices for pop and classical. If you look on the left, you see 2 PDFs, one from pop, one from classical, both assuming the distance between the previous and the current note is a distance of 1. You'll notice there's very high probabilities associated with few indices in the scale, and very low probabilities associated with many indices. That's an indication there's very low entropy to this model, and therefore a very strong indication of developing a very meaningful model as opposed to modeling random noise. Currently we have a desktop web application developed, but there's associated pros and cons with developing either a desktop application or a mobile application. Therefore, we believe it's important in the future to develop a mobile application as well to maximize our user base. And here you can see a current version of our prototype. Users select a variety of inputs. Those inputs being the scale, qualified by the root note of the scale, as well as whether the scale is a major or minor. They can select tempo, which dictates how fast the melody plays. They can also select meter, which is a qualifier on the type of rhythm played. Lastly, they can select a chord progression, which associates a chord with each measure of the melody. With those inputs, they can repeatedly generate melodies until they find one they like.
Here's the basic structure of our team. Colin, with the most background in music theory, was able to design the melody-generating structures which we wanted to integrate into code. I, with my interdisciplinary knowledge, was able to translate that information into workable code, where Austin, with his computer science background, was able to work on it and develop the full product. Secondarily, Colin handled most of the external contact with teams such as the legal team that we've been in communication with, and then Austin and I worked on the product back end and front end. Here are the list of applicable standards relevant to the project. Because we're outputting MIDI files already, we are compliant with the MIDI standard. And then because Ripple is not a safety critical software, we are compliant with software safety. Not yet applicable is all standards that could be applicable in the future as we work on this project past this year. If we decide to keep user information, we'll need to keep data private. If we look for a potential acquisition as an exit option, we'll need to create documentation for that process. And then if we decide to move to a mobile platform, we'll need to comply with mobile audio. And then there is the legal issue of the possible generation of a copywritten melody. We have been in discussion with our legal team, primarily Colin was point of contact for that. And we have found a resolution. If you visit us during the post-presentation, we will be happy to explain it in further detail. Here is our bill of materials. There was not a whole lot that we needed here. There was a MIDI to USB converter, which we needed in order to communicate with our hardware for tests, but we borrowed a MIDI keyboard from Professor Deliwala, so there was no expense. And then finally, to wrap up the presentation, I want to talk about the entrepreneurial potential as we move into the future. Throughout the course of the year, we have worked on developing some IP for both the product and the algorithm. And then once we have that protection set, we want to look towards further potential for the application of this algorithm. We want to look into more complicated genres such as jazz, and we want to extend the capabilities to, rather than generating melodies, we want to generate full songs. And then, as before, there are some possible other platforms that we can pursue. We want to look into a mobile ringtone generator as another possible product, and we also could potentially expand our website to that of a social media page for composers to interact and connect with each other. Finally, an additional exit option, as opposed to acquisition, we could go for a licensing option in the future.
Thank you very much for your time. Please visit us during our expo presentation. And you can also test the product if you want to yourself.
Hi everyone, we are ProTags, and we created an autonomous gating system for proton therapy. We are an interdisciplinary team where Ahmad and myself, both electrical engineering majors, David is a computer engineering major, Karen is a computer science major, and Max is a systems engineering major. Our advisors are Dr. Insuk Lee and Dr. James Weimer, and we are also provided help from Dr. Jose Luna and Dr. Eric Diffenderfer. So proton therapy is generally used for terminally ill cancer patients. It's also typically viewed as terminally ill cancer patients' last resort. I'll recheck that. But so then a proton is then accelerated up to 60% of the speed of light and then fired directly at the tumor in order to fry the tumor. Currently, the procedure requires a radiation oncologist to manually turn on or off the beam in order to prevent the beam from damaging surrounding tissue. While this is going on, the patient is monitored through the use of a breathing apparatus so that the clinician can make sure their lung volume is okay. If a patient does have lung cancer, every time the patient breathes, the tumor moves, which makes it extremely hard for the oncologist to pinpoint exactly where the tumor is. Due to this problem, 20 to 25% of patients experience damage to surrounding tissue, which can often lead to fatalities. Therefore, we wanted to create a new autonomous gating system that will reduce error in clinician responsibility, increase the comfort for the patient, and give feedback to the supervising clinician about the patient status and the system status. We considered 3 different options in order to complete our objectives. We thought we could employ a motion capture system combined with a pulse oximeter to get the necessary breathing information, or we could combine a pulse oximeter with a chest strap sensor, and lastly, we thought about using a medical-grade respiration sensor instead of building our own. Next, I will pass it off to Ahmad, who will go over the total system design and go into the hardware design.
Thanks, AJ. So, take a look at our overall system architecture. We have 2 sensors tracking the patient's data. We have a pulse oximeter for measuring the BPM, and a chest strap for measuring the movement of the chest cavity. So the chest strap creates a small voltage difference, which we amplify using an instrumentation amplifier, and then filter using the low-pass filter. The microcontroller collects these 2 data points and converts them as a CSV to the PC, which does data analysis and determines when to turn the machine on and off. The PC communicates this information back to the microcontroller, which then triggers the proton therapy machine and turns the power off. Take a look at our hardware design. We created a chest strap made out of an elastic band with a variable conductive rubber cord. Then we used an AB620 instrumentation amplifier to amplify the voltage change over a voltage divider. And then the pulse oximeter that we were using outputs an analog output from 0 to 1 volt that maps the patient's heart rate from 0 to 250 beats per minute. Finally, the microcontroller reads these 2 values and prints them as a CSV through serial. The proton therapy machine is then interfaced using the DB9 connector, which allows us to turn the machine on and off when the tumor comes in and out of the line. I'm going to hand it off to Nadeed, who will talk to you about our software design.
Thanks so much. So our software flow is made up of 3 main components: a calibration state, the gating state, and then a friendly GUI through which the clinician can interface with the system and with the machine. The calibration state involves us asking the patient to breathe deeply for 30 seconds so we can calibrate what their baseline heart rate is, as well as their chest expansion, as every patient is different. So here you can see the BPM data of the patient, and then from this we can figure out what their baseline heart rate is. And here's the chest strap data. At the bottom you can see where the local minima represent where the patient has where the patient breathes in and the chest is expanding. Through some data analysis, we then figure out what the average minimum is, so we can have also a baseline minimum as to when to trigger the machine. So then we move on to the gating state. In this state, we perform some real-time data analysis on the chest strap data as well as the pulse oximeter data to trigger and kill the machine, as Ahmad has mentioned before. We use the chest strap data mainly to trigger the machine for us to know when the patient is ready to be when the machine is ready to be triggered, and then we use the heart rate to predict when the patient's going to let go of the breath and turn the machine off. So now I'll hand it off to Karen, who will talk about project management.
So the project management was essentially divided into software and hardware components. So Ahmad was in charge of interfacing our system with the proton therapy machine. Ahmad and David were also in charge of getting the data from the pulse oximeter and chest strap, so that the rest of us can analyze and normalize, access the GUI interface, and everyone was in charge of doing research and also administration. So now I'll talk about the budget. The chest strap was $24. The pulse oximeter was for $165. The data collection, which includes the particle photon and instrumentation amplifier, was $20. So the total cost for the project was $610. However, because we were provided with a pulse oximeter and also the particle photon and instrumentation amplifier, our total cost for us was $25. So now I'll pass it out to Max, who will talk about the standards.
Thanks, Karen. So I'm going to talk to you guys about some of the most important standards and specifications that relate to our project. First, HIPAA sets the standard for the protection of patient data. Our calibration state is constantly reading in patient data to be used later in our triggering and killing the machine. So we ensure that this data is secured locally and is not misused in any way. Next, we move on to the IEC 62304 standard. This determines the life cycle requirements for the development of software for medical devices. Our software system depends on algorithms we implemented and minimal interactions with third-party libraries, which ensures a robust system in the long run. Next, we have the IEC 60601 standard for medical electrical equipment. Our circuit is sealed inside of a plastic container to ensure the basic safety and the essential performance. The machine is not compromised. Next, we have USB standard for communicating and relaying the data we collect between the microcontroller to our engine that runs on a local computer for this is our current system. And then finally, the IBA UBTI specifications determine the beam triggering interface for the proton therapy machine, which helped us, which was important for us to understand in order to successfully trigger or kill the machine. Looking forward, we are confident that Dr. James Weimer will use the algorithms and software system that we implemented in order to ensure the efficacy and comfortability of proton therapy for future patients. Thank you.
Everybody needs some time to score. Are we ready?
Let's go.
Yeah, what do you think? Let's go.
Okay, so hi guys, my name is Brittany and this is my partner Olivia, and we're Team 11 Neon Analytics. And our project focuses on analyzing the data that was taken from the Neonor, which is a previous new design project. And the Neonor is a bottle that has a pressure sensor built into it, and what it does is it tracks the sucking and swallowing pressure of a baby's feeding pattern. So some of the original objectives of our design were to analyze the longitudinal changes in the baby's feeding pattern, in a full-term baby's feeding pattern, because we had 3 different groups to analyze. We had full-term babies, premature babies, and babies born from opioid-addicted mothers who are also premature. So we were going to analyze some of the longitudinal data taken for the full-term babies over time, and then point out some of the differences between these full-term babies and the premature babies. After we did this, we wanted to pick a key signal that we thought represented a good, healthy baby, and then look at some of the longitudinal changes of the babies to see if they were getting towards that key signal or to see if they were reaching health. So some of the problems with our original design was that longitudinal data was not available for all of the signals that we had, and also there wasn't enough data to make a good conclusion because there were only 30 to 40 set data points per set, so we couldn't make a real conclusive analysis. Also, not all of the signals that we received were usable because of multiple reasons. Like if the baby wasn't hungry, sometimes it would just pick the nipple and it wouldn't feed correctly, so the signal would become messed up or stopped, like shown in the example. And lastly, we discovered that the health is not necessarily determined by whether the baby was born full-term or premature, as a lot of premature children had healthy signals by the time that they were recorded, so their feeding patterns were up to par. So instead, our final design focused on looking into the transient or the abrupt changes in all the signals, and then also taking a continuous wavelet analysis so that we could separate the signals by different groups and group them into similarities. So since this design process was all data-based, we signals, and this project was of no cost to us. And our project abides by the HIPAA privacy law, and it makes sure that no data or information of the patients can be tracked. And we're also sure that the NEONOR abides by the ISO law and the medical device is in fact quality and of good use. And because we're only a two-person team, it was not too hard to work with project management. Olivia focused mainly on the quantitative analyses of the Morley analysis, and I focused on the qualitative analyses of grouping the signals by similarities. And we met bi-weekly with our advisor to make sure that we were compiling our data and that everyone was on the same page.
So the conclusions that we came to resulted from using a continuous wave Morley transform, as we mentioned, and examining the time frequency analysis on our data. And we found out that the prominent frequencies in between both subsets of the preterm baby and the full-term babies range between 0.8 to 1.5, and that there's some data that we found out with comparing the expressive pressure and the suction pressure within the full-term baby and preterm baby are different due to the stages in their life that they were taken at. With the preterm babies, the signals were taken 3 to 4 weeks after they were born, when they were ready to be released from the hospital, and the full-term babies were taken 1 to 2 days after they were born. The next slide shows an example of the analysis we've done on our data. The first row shows the example of a full-term baby, and it shows that the regular signal plotted, looking at the peak pressures, and just looking at the transients that occur, and the magnitude scale. As we can see, the magnitude for the full-term babies tend to be concentrated in a subsection of the signal, while compared to the preterm baby on the second row, where the signal is more consistently spread out. And this is due to the fact that the preterm baby has a more developed feeding behavior because this is ready to be released from the hospital compared to the full-term baby, which was taken 1 to 2 days. The next slide shows an example of the subsets of both groups. And the first row shows that the transient sums for the preterm babies are more concentrated compared to the full-term babies, where it's more spread out. This is due to transient sums and abrupt changes in the signals, and this is due to the more developed feeding behavior of the preterm baby compared to the full-term baby. But on the bottom, you can see that the prominent frequencies in the full-term babies tend to be more concentrated compared to the preterm baby. As you can see, the outlier at the 2 is due to the fact that that signal wasn't actually really hungry at that time, so their prominent frequency doesn't portray the actual prominent frequency of a regular feeding behavior. And also, we don't have enough data from the preterm baby to have a full conclusion from it, but they tend to have the same range in prominent frequency. This is an example of how we analyze our data. The first row is just the regular signal. The second row shows us a detrended signal, so that we're not focused on any nonlinear trends within the signal. And the third row allows us to examine the signal which is reconstructed from using the continuous waveform transform to not be distracted by any random frequencies that aren't within the range of our sucking behavior. This is an example of MATLAB code that shows that the full-term babies tend to have stronger stalling pressure compared to the preterm babies, as the full-term babies tend to have a stronger developed jaw compared to the full-term babies. And this leads us to our future suggestions for our data in the future and how it can be used.
So we just have a few future suggestions. So one of the suggestions that we really want for the next researchers that take on this project is that more data be collected from the NEONOR so that a more conclusive analysis can be drawn. And we'd also like to make sure that more longitudinal data is taken, and also that future data is taken from these babies so that we can see if their health statuses match up with our analyses, making sure that this future data is still protected by the HIPAA privacy law and that it can't be tracked back to the patient. Lastly, we would just want to add a breathing sensor to the bottle, as we feel that the breathing will have a large part to play in the baby sucking. And we would just like the data to all be compiled readily so that it can be looked at side by side, as the format in which we received the data was a bit messy at first and hard to analyze. So there we go. Thank you so much.
Hello everyone, we're Team 16 D-Cortex, and it's me, Semi, and my friends Matt and Jacob. And in the past 2 semesters, we worked on this product where we hope to decode the relationship between brain signals and motor tasks, and essentially build a product that does the machine learning part as well as the visualizations.
So we have access to a state-of-the-art fMRI dataset from the Human Connectome project. And basically the experiment that's been done is a subject lies down in an fMRI machine, and every now and then you ask the subject to perform a motor task, like lift your right hand or lift your left foot. And what we're doing is building what's called a task state decoder. So it's an algorithm which takes as input the signal from fMRI and produces as output for every moment in time a class prediction, so which motor task was performed, if any, at this instance. And fMRI is a brain imaging technology which is sensitive to differences in the magnetic property of matter. So it turns out that blood which is rich in oxygen has a different magnetic profile from blood that's not rich in oxygen. And so the idea is that when a subject is performing a motor task, certain parts of the brain start consuming more oxygen. And so since fMRI can pick up on blood oxygen content, our machine learning model can start to learn how different metabolic patterns in the brain correspond to different motor tasks. And in terms of standards, really the big one is making sure we satisfy patient privacy, and that's the HIPAA. So we want to make sure the data is kept anonymous. And we're trying to follow software best practices and making sure we abide by open source software clauses.
Let's talk about the design aspects a little bit. So the first thing we do after we obtain the fMRI data is pre-process it to get rid of any effects of heart rate and respiration. Because for a motor task, we don't really need those. Like lifting your right arm doesn't really make your heart go faster. But let's say if in another case, if we were to test for like gambling and see whether someone's bluffing or not, we would not do that, for example. But like essentially, the algorithm can be designed for different purposes. After the pre-processing part, we encode our data to a format that we can actually use in our classifier, and then we perform feature selection, which is, of all the brain signals we have, which ones do we want to use, and which ones are just superfluous. Afterwards, we're ready with our data, and then we can feed it to our neural network classifier. And after a certain amount of training, our model is now ready to analyze any new incoming fresh fMRI data. And for this fresh data, that's not labeled, so it doesn't tell you where like the patient is, let's say, moving their tongue or like moving their right foot. It basically gives us for all time steps whether this person is doing anything or not doing anything, which is then fed into our front end for visualization.
So here we'd like to give a brief demo of our prompt.
Copy the link.
You can escape and go to...
Oh, we're allowed?
Yeah.
It's like a YouTube link. So we'll show more during the demo session, but just to give you a brief taste of what it looks like.
So basically here we see the visual interface where we have a 3D image of the brain where we used we had the exam third-party libraries for visualization. So here we asked our classifier for a patient that our classifier had never seen before, how is our classifier going to predict what task was being performed at given any time in the disease. So here we can see that this was a patient for and a time interval for more than 5 minutes, and we can see how different regions of the brain actually light up as time in disease go along. So we hit our predictions to first show how it was changing, and we can see that the blues being the actual time of the disease where a patient was actually performing some motor task, and the reds being our predictions. And we can see the class labels here. So as the time moves along, we can see that not only we were able to give with a certain level of accuracy, where it turns out to be high, very low 90s, we can exactly say what kind of a motor task was being performed at given any time indices within less than 1.5 seconds delay. So we think that that's really powerful, but also we see that sometimes we missed some of them, and let's not forget that this was a patient where our classifier had never seen before. So it was able to adapt from previous patients to newer patients, so that was powerful. So one more thing to add here is that we see a one false activation. So we could have just asked our classifier when a task was being performed, what kind of task was being performed. But we also did for the entire time sample where nothing was being performed, we still asked our classifier what was being performed. So that means that the classifier was able to guess when nothing was actually being performed. The classifier can accurately say, okay, actually this patient is not doing anything. So in terms of that, we can see a high level of accuracy. And to very briefly talk about our performance, so our product comes with a built-in classifier, and we can see that we have, for the majority of the motor tasks, we do have a good level of precision. And for when we talk about the confusion matrix, when we look at the diagonal, we can see that there's a really high trend. Moreover, we can see that we're really good at distinguishing between different kinds of motor tasks, but it's really hard to pick up it's really hard to pick up when there's no action and there's a less powerful signal.
So, but like, why D-Cortex? What does this product promise? So, when we came up with D-Cortex, we had mainly two ideas in mind. The first was in prosthetics. So, current state of prosthetics, at least the commercialized versions, mostly rely on active participation. So, it's not exactly natural, like a patient doesn't move their left hand as we would do without any thinking. But if we can accurately predict motor tasks in real time, that means we can build human-computer interfaces that allow us to build smarter prosthetic devices that work on the basis of just recognizing this signal that comes from the brain, which is very promising. And the second application could be possibly diagnostics, which means the capabilities of D-Cortex are not necessarily limited to motor tasks, and as we said, like, we can apply these things to gambling or like emotional stimuli. So the use space for D-Cortex is actually pretty vast. So we are D-Cortex, and thanks for listening to us.
Let's go.
Hi everyone, we are Team 12, Wi-Fi++. I'm Deb, here are my teammates Mauricio, Jack, and Sinead. Our advisor is Dr. Jorge Santiago. Now, Wi-Fi++ is a wireless communication system that allows devices to transfer data over visible light. It easily interfaces with other electronic products, allowing them to start sending data over light as well. And to understand why we built something like this, you need to understand NFC, Near Field Communication. This is a very popular wireless communication protocol built into a lot of modern devices, including most smartphones. Some of its many use cases include Apple Pay, Samsung S-Beam, and Nintendo Amiibo. However, NFC suffers from some severe limitations in its strict alignment requirements and low range. In fact, the NFC ports on two devices practically have to touch for them to communicate, as seen in that picture above. Additionally, it gives off RF emissions that makes it unsuitable for electromagnetic interference-sensitive environments. On the other hand, our Li-Fi++ optical communication system is an alternative to NFC. It boasts higher range, but similar speed and relaxed alignment requirements, overcoming some of these severe limitations. In addition, it only gives off optical emissions, not RF, making it suitable for these EMI-sensitive environments. Now, the core of our product is the bidirectional wireless optical link. This easily interfaces with other electronic devices through UART, a standardized serial communication protocol built into most microcontrollers. This means that other electronics manufacturers can integrate our product into their own devices, such as POS systems, smartphones, and more, and allow them to communicate over light. We also developed a link layer networking protocol that ensures reliable transmission of data over our light link in the case of loss or data corruption. And we built a couple of sample applications on top of our product, including a Bluetooth to light bridge that allows existing Bluetooth-enabled devices to connect to our device without any additional cabling needed, and then start sending data over light, as well as a file transfer protocol that reliably transfers arbitrary files over our link. I'm going to hand it off to Mauricio.
Thank you. So these are our system specifications. The transceiver will operate at a range of approximately 20 centimeters and transmit data at least 57.6 kilobits reliably. It will use approximately 150 milliwatts of power and communicate with other devices through UART, as mentioned before. This is our design overview. As you can see, the transceiver is connected to a device which is a PC or microcontroller, from which it receives a UART signal. It will convert that into a light signal, and at the same time receive a light signal from the other transceiver and convert that into a UART signal back to the connected device. So in a typical application, we may have the transceiver connected to a microcontroller and the microcontroller connected to the phone through Bluetooth. This is the Bluetooth to light bridge mentioned before, and this enables two phones to talk to each other through Wi-Fi. So our current design has two devices talking directly with each other. In this sense, it is like the NFC system. However, we did previously consider a different many-to-one design, where instead we'd have like one central hub connected to many others. In this sense, it would be more like a Zigbee design, which is a similar system that uses RF instead of light. However, this did have major design difficulties, such as a precise scheduling algorithm that would be required when communicating with the hub, as well as concerns about multiple light channels interfering, so we decided to follow the NFC-like current design. I'll pass this off to Jack.
Okay, so before we could send data over a light link, we first had to write some software to do so. So the first thing we wrote was a serial communications driver in Python to send data as raw UART over our light link. The next thing we wrote was a Bluetooth driver that allows us to connect our phones to the link and send data over. And the last thing, and most recent thing what we wrote, is a link layer networking protocol that, as Deb said earlier, allows us to reliably transmit data over our link. This is also written in Python, but theoretically could be ported to other languages and devices as well, as long as they're compatible with the UART standard. Now for our hardware, for our transmit circuit, it consists of an LED driven by this transistor here. So the transistor turns the LED on and off according to the UART signal coming in. And the light from the LED goes over to that diode over there. The diode signal is amplified by this amplifier, a trans-impedance amplifier. That's sent to the comparator net, and the result signal over here is sent to the microcontroller for further processing. Now for our budget or bill of materials, we expect the product to cost around $110 with the Raspberry Pis and $40 without. We quoted both figures because we envision selling this product not only to ordinary consumers who would want a more packaged design, but also to manufacturers and hobbyists who wouldn't necessarily need the Pis. So we do envision that the price will drop significantly if we were to sell this to larger manufacturers due to economies of scale. And now I'm going to pass it on to Sinead for standards.
Okay, thank you, Jack. So in terms of the casing of our product, our transmitter and receiver is enclosed in a case made out of black acrylic material. The reason why we chose black acrylic is because to minimize light interference, and also acrylic is non-flammable. We laser cut this acrylic material and press fit it together to form the cases for our product. Now moving on to standards, since our product does revolve around light, we have to adhere to the light emission standards. Our system is low powered and therefore poses no risk of injury to the retina or to your eye, for instance. As mentioned above, we are using UART standard protocols as well as commercial Bluetooth devices that adhere to the FCC Part 15 emission standards. And lastly, talking about our IEEE Li-Fi standard, this standard is outdated and not used in many Li-Fi companies and therefore does not pertain to our project. In terms of project management, all team members worked on all the different aspects of the project throughout the entire life cycle. However, each one of us decided to spearhead or lead a certain aspect, and the following team members helped on each design aspect. So for instance, in terms of hardware design, Dev and Jack led that area. In terms of embedded software, Lucio and Jack led that area, and I took charge of the case design. So thank you everyone. I hope you enjoyed listening to our presentation about Li-Fi++, and we're looking forward to see you down on the expo to learn more.
You're on.
Hi guys, we're Remote Ranger. I'm William, this is Rowan, this is Carter. We were advised by Tanya Khanna, and we're going to tell you about a project today. So there's over 280 million hikers a year that go into national parks, and it can be kind of dangerous because you're going to remote areas, and 160 actually end up getting killed or lost in hikes. The national park has to do 350 forest ranger search and rescues a year, and it costs almost $5 million to the national park budget. So our solution, we're trying to provide a low-cost tracking beacon for hikers. We're trying to significantly improve the efficiency of search and rescue operations with directed search, because actually over half the time spent at search and rescue operations is just trying to locate the hiker. And we're trying to provide a significant cost savings to national parks with reduced loss of life. So our device, we wanted to provide location tracking to hikers in remote areas, specifically where cellular networks wouldn't be available or other mainstream radio frequencies. And then we wanted to replace the outdated paper system. So if you go to a national park right now, you get a little tag. It writes your emergency contact information, where you're planning on hiking, what time-ish you're planning on getting back, but that's it. And then you just keep it on your backpack. So basically it's a way to find your body, to be really morbid. And we want to make this affordable for national park as it is a public service, and be effective, just at saving lives and finding them. So our specifications, we wanted a device that could ping the GPS location every 10 minutes. Because hikes are generally multi-day in backcountry woods, we wanted a multi-day battery life. And we wanted it to be ergonomic and lightweight. When you're doing hikes, you're generally very concerned about weight because you're carrying what you have. And then additionally, we wanted it to be able to communicate 30 to 50 kilometers from the beacon to a network tower. So I'm going to hand it off to Garner.
So basically one of the first decisions we had to make was what network style we were going to use. And on the left you can see we can do a high frequency setup that gives you pretty much very high bandwidth to work with, but at the same time each node's and each hiker's individual range is very short. So if you apply that to a national park, that means each unit basically can talk maybe a kilometer or so at most, and you need nodes set up throughout the park, so that wasn't too efficient for the network we wanted. On the other hand, you could do an AM or FM frequency, which gets you tons of range and high bandwidth as well. But then at the same time, each hiker would need a pretty big battery, and that would really affect the amount of battery life that we needed, because we really need at least 7 days to make this very useful for hikers. So we decided on something in the middle on the network called Sigfox that operates at about 900 megahertz. There's low bandwidth, but at the same time, we're just transmitting GPS information and the device ID to identify the hiker. So that's only about 12 bytes that we're sending, so that worked out perfectly. You get high individual range as well. In rural environments, it's about 30 to 50 kilometers. So there are a few nodes you need to set up throughout the park, but it's much more efficient than a high frequency setup, and it's designed to. So the system design for the actual board we're using is based on a YSOL Sigfox module. So what that does is it locks your GPS location, sends that to our microcontroller, which then parses GPS data into 3-byte payloads for both your longitude and latitude. So basically 6 bytes total for your GPS location. It sends that back to the YSOL module, which then communicates over to Sigfox. Sigfox network picks that up on the back end, and then we do a little more with that there. We have the device ID to identify the hiker, and then we have an AWS app that can help the park rangers visualize where hikers are, how long it's been since they've last seen a communication ping from them. So has it been 2 days since we've heard anything from this hiker? Maybe we should go look for him. And you can see a live location tracking of where this hiker's going. So you can tell if they're going off path, if they're stuck in the same place. Basically anything that might cause a concern, you can see that on your screen. And basically just to show you how we got from September to today, we started with the initial plan to choose Sigfox as our protocol. We worked on a YSOL dev kit that had basically everything you want from it: GPS, Wi-Fi, Bluetooth, altitude, temperature, whole tons of things, so we could work with anything we wanted to. Worked on that towards our fall demo, and then in the spring we moved to a smaller board that has a much smaller antenna as well. So the original antenna was about 5 or 6 inches, which doesn't really fit well on a backpack. The new antenna is even smaller than a rubber eraser that you would use. And it has GPS and is about the size of a playing card. So we worked on that, also minimizing how much GPS data we were sending to fit within the Sigfox parameters, and we arrived to our final demo today.
So moving into the industry standards and ethical considerations of our project. First off, our device transmits at 915 megahertz. So this puts us in the unlicensed ultra-narrow band between 902 and 928 megahertz. Because we built our product on Sigfox's platform, we implicitly comply with all the FCC regulations about transmitting at this frequency. Additionally, we're limited to having a 50 millivolt electric field strength at a 3-meter radius from our device. But since it's a low power application, we also adhere to this. Lastly, we have to look at regulations regarding the usage of batteries. So these basically are involved with the safe discharging, recharging, and handling of batteries, including things like any physical stresses they may come into contact with, or what would happen in the event of a fire. Ethically, we're trying to improve the efficiency of search and rescue, right, which impacts lives. So it's crucial that we have accurate GPS data and a long-lasting battery life, because if either of these things were to fail, it would actually be counterproductive for rangers if we were to mislead them or not give them the information that we promised. Yeah, so looking at the bill of materials, basically this kind of outlines our move from the original dev kit, which had a lot of extra protocols that we don't really need, to our smaller board that we're using this semester, including all the debugging things that we used to code. We also used the power circuit you can see here was the lithium-ion battery, which was at 3.7 volts, and then a battery boosting circuit that brought that voltage from 3.7 up to a 5.2 that are working efficiently used. Moving into the future applications future work and applications. Basically, extensions of this project that we saw, we're adding a kinetic or solar charger to kind of take advantage of the fact that hikers are moving around. Adding some kind of communication system to ping local hikers in the event of a distress call. This would just increase the time, or lower the time for the first response for search and rescue. Additionally, this device can be adapted for different kind of natural disasters like hurricanes and forest fires, and then also extending the mobile app past what it currently is, so family and friends can access basically what their hiker loved ones are up to. Thanks.
Okay, guys, you're on.
Good morning, everyone. We are Team 9, or Boston Optimized Healthcare. My name is Carolyn. I am here with Brian, JJ, Adam, and Dylan. Our advisor for this project is Dr. Barry Silverman. To start, I would just like to walk you through our team dynamics and project management. We are a 5-member team, so in order to operate as efficiently as possible, we decided to break our project management up into 4 main functionalities: design, data analytics, software development, and deliverables. Each team member took on 2 main functional roles. And now I'd like to pass it off to Adam.
Thanks, Caroline. So the problem is that there's a misallocation of resources in the public health services today, and the improper usage of them primarily resides in the emergency department. Our project focuses on elderly people who are chronically ill and have low incomes. And this is important because if you take a look at the graphics up here, on the right you see low income area in Boston, and on the left you see avoidable ER visits in the same area. And you see that there's a high correlation between the two. Our project focuses on elderly people who are chronically ill and have low income. And the key stakeholders in our project are medical and political institutions, hospitals, individuals, and corporations. And now I'm going to pass it off to Dylan to talk about our design objectives.
So the main objective of our project was to create an accurate model of how these elderly, chronically ill people actually interact with the healthcare system. The goal is that if we can understand this, we can look at alternative care services and see how they impact the cost and the efficacy of care on the people, ideally to find lower cost services with higher quality of care. In order to do so, we used agent-based modeling methods. Agent-based modeling methods on a high level is just creating a micro-scale model of how these individual agents are going to interact with the system, and then if we look across a diverse population, we get a good macro-scale picture of what's going on in the system. This is often been talked about in systems engineering literature as a potential method to actually implement one of these models, yet we haven't found any actually implemented in practice, so this is one of the first attempts to do so. We use data from the National Health and Aging Trend Study in the U.S. Census to actually estimate the parameters for our agents that are modeled specific to the Boston region, and we were constrained to just use Boston data for elderly people. And we, as like complexity rises, we try to include more chronic illnesses. We only consider the 5 most prevalent chronic illnesses in the population. So originally we had a different type of model where we were looking at just a single treatment option, which is the traditional healthcare system, but we attempted to model the actual transportation system of Boston. So we were using NetLogo, which allowed us to model the cityscape of Boston and actually see, try to offer alternative services such as like mobile health services that can actually go visit people. However, the complexity of that was really high, and it didn't allow us to actually look at simpler alternative care options. So we switched our model over to a new software called AnyLogic, which allowed us to model a more complex model state and allowed us to very easily interchange new alternative healthcare services. It also allowed us to more easily model custom distributions of parameters for our agents.
So the overall design of our project can be described as the container or the environment in which the problem lives. This design is simplified from the real-world system. However, these assumptions we're making are crucial to eventually implementing our model. So we start here with an elderly patient or an agent, and they seek treatment. They can either enter the health system or get alternative treatment options. By entering the health system, this is where the fundamental inefficiency in the system lies. So a patient will receive care, and they can either become healthy, need more treatment, or die. The probability of a patient becoming healthy is extremely low because we are looking at a demographic of chronically ill patients. Because of this, agents will be stuck in this inner loop, which is costly for both the hospital and the patient. The alternative treatment options provides a way for the patients to avoid the health system. So in order to reduce the overall cost of this system, we need to divert patients away from entering the health system and towards alternative treatment options. And now I'm going to pass it off to JJ to walk you through the functionality.
Thank you, Carolyn. So you may ask, how did we tackle this problem? Well, we started by creating agents, and we made them intelligent. Our decision tree was driven by internal agent parameters that we set from real-world data, including income distributions, real-world statistics on gender, chronic conditions that people had, all derived from NHATS and census data. And we also set dynamic variables, such as health level, willingness to seek care, and out-of-pocket costs. These were all incorporated into a utility function given to every agent to correspond with their decision tree. The agent would take the route that would maximize their level of care and minimize the total cost. So here's an example of a simplified version of our state chart inside of AnyLogic. Here, a healthy patient, upon being diagnosed with a chronically ill condition, has two options. They can either enter the traditional health system or seek alternative care. Each of these options are associated with different benefits and costs, which modify the internal variables on the agent. So what we do in our software is analyze 1,000 of these agents and derive useful parameters that policymakers can use to make decisions based on stuff they said in the beginning. And I'm going to pass it off to Ellen.
So in terms of our data, we had three primary considerations. First, the data is only from patients who reported their information publicly, which isn't necessarily representative of the larger patient population. Second, we also have to consider that hospitals with novel medical techniques don't always disclose the costs and efficacies with these novel practices with the highest degree of accuracy, given that they're novel. And last, we have to consider that patients have external influences, such as taking preventative care on their own or deleterious actions that can potentially harm their health. Now, in terms of standards, interoperability standards with our simulation are taken care of because we're using AnyLogic, which can work cross-platform. AnyLogic is a Java-based software typically used in supply chains and logistics. In our case, we're using it in healthcare policy planning. In terms of end-to-end information flow, the protected health information that we're using is publicly available for research purposes, so we don't run into any issues associated with that. And last, we're following all lifecycle management policy guidelines governing the relationships between agents. We look forward to answering your questions later this afternoon, demoing our model, and demonstrating our results. Thank you.
Yep, good. Hi everyone, thank you all for coming. We're super thrilled to be sharing what we've been working on this last semester and a half. I want to start out with a couple of questions. How much of our data, that is data that belongs to us or that defines who we are, can we access through our phone or our computer? And the answer is a lot. You know, I can see my friend circle on something like Facebook. I can see my credentials on something like LinkedIn, my emails and messages on Google. Now I want you to ask yourself, how much of that same data would we be able to access if we were to turn off the cloud or not use any of these applications? How much of that data can we retain that is ours, truly ours? And the answer there is not very much. If you think about the internet today, it's run by a few large companies, your Facebooks, your Amazons, your Googles of the world. And if you think about how they've extracted value, it's largely in the form of proprietary databases, where they store our information, where they exploit that information to then sell to third-party providers or influence our behavior. And so this comes at a cost. One, security, think Equifax data breach. Two, just a complete lack of data ownership. I'm not able to migrate from application to application. And three, exploitation, think Equifax data breach. Now imagine a world where the data is brought back to the users, where using a self-sovereign identity system, I am able to access these applications who no longer store my data, where I'm in complete control. And so that's what we've been working on. We've been working on trying to shift the narrative back to a decentralized ethos. We've been working on finding ways to do that in the simplest of applications. And so Mark will present what we've been working on.
So looking at all these issues with today's internet, we chose to focus specifically on messaging because it plays such a crucial role in the way that people communicate and interact in today's world. So we built a messenger on top of Blockstack, which is a new internet for decentralized apps that's meant to eliminate some of the biggest issues with centralized messengers. The first issue being the lack of interoperability. So for example, if I'm using Groupie, I can't message with someone on Facebook Messenger or any other messaging app. The second issue being the lack of data ownership. So whenever you create an account with a company like Facebook, they technically have access to all of your data, and we've seen this specifically recently with Facebook. So to solve these issues, we built our app on top of Blockstack, which as I mentioned is decentralized, and this means that all users own their own data and can control who they share it with, so that solves the data ownership issue. In addition, we built the app in a way on top of the Blockstack protocol so that someone using Blockchat could potentially message with someone using a completely different messaging app on Blockstack, and this allows interoperability between messaging apps.
So in terms of design, we made two critical choices. First was we used a decentralized ecosystem that Mark mentioned called Blockstack. So Blockstack does two things. It decentralizes identity and decentralizes storage. So if you think about identity, traditionally all identity has been controlled by some centralized body, whether that's social security that's sort of governed by the government, or whether that's your Facebook ID that's governed by Facebook. What Blockstack allows you to do is it stores everyone's identity on a node that everyone has. So it essentially everyone's managing the identity and there's no centralized body. That really allows your identity to be secure and it allows it to be truly yours. Secondly, it also decentralizes storage. So traditionally when you're messaging on Facebook Messenger, all your messages are stored in the Facebook database. In a Facebook data center somewhere around the world. However, with Blockstack, you can actually plug in your own data source that's completely encrypted that allows for true data ownership. And then how blockchain technology is integrated with all this is that it stores pointers of everyone's identity to their storage. That allows for a truly great ecosystem for building decentralized applications. And our second design choice is standardization. So instead of forcing users to use our user interface for messaging that we created, or our features that we wanted, we created a standardized way of reading and writing messages on a JSON file. So any developer could create their own application on top of our standard and allow, for example, if Andrew creates an app on top of our standard, that we can communicate using his app and my app together. So it's not just using our features.
As alluded to several times now, we chose Blockstack specifically because it was advantageous to us because of how much it already provided in its inherent layer. Ethereum was an option, but it doesn't provide the actual authentication standard that we have, need rather. And also, there were other options that required us to create either our own blockchain layer or revert back to a database structure. Essentially, we already had the foundation of the house built for us, we just had to build the house.
So our standards are divided as follows. The first layer, Blockchat, plus the Blockstack browser it's built with, and the second layer is the blockchain, which Blockstack uses to achieve consensus and decentralization. These are again divided into two columns, technological on the left and the legal ethical on the right. So on our platform, in order for users to message, user A has to agree to share their data with user B. But who creates and distributes these user profiles? Who gets to write the contracts that the users have to sign to share data? The Blockchat naming system, or BNS for short, standardizes these issues of identity and data sharing. Shifting to the right side of the first layer, some of you may have heard of the new EU data privacy laws coming into effect this year. They include provisions like having the right to ask a company to erase your personal data. These laws do not apply to Blockchat in the traditional sense because users' data is stored in their own storage and not some Blockchat data center. Because this is a messaging platform, there is the inherent risk that users may use our app for malicious reasons like cyberbullying. As we move forward with this project, we will continue to ideate on ways to mitigate this. Shifting down to the blockchain layer, consensus standards, specifically Bitcoin's proof of work, are actually incredibly pertinent to our project because adherence to these standards maintains the security of our messaging. Let's say that some miner had 51% of the mining power and planned to use that to maliciously alter the creation of new blocks. In the same way that the security of your Bitcoin wallet would be threatened, so too would the security of our messaging app. I want to thank everyone for coming out to listen to our presentation today. and would like to invite you to come and try out our demo later in the afternoon. Thank you.
Thank you.
Hi, I'm Kelly. This is Cody, Julia, and Ashley, and we're Team Footsies. We built an electromechanical shoe to help combat trauma. We don't live spirits, we live souls. We're an interdisciplinary team of 2 electrical engineers and 2 mechanical engineers, giving us a very wide skill set. With this in mind, we really wanted to make a product that would have an impact on the community, and we thought medical devices were perfect for this.
So we started by talking to family and friends that had foot or leg related injuries and followed them throughout the recovery process from their primary doctor and specialist through their physical therapist and orthoptist. In addition, we followed up with a lot of conversations with our advisors, clinicians, and gait researchers while developing our project based on foot drop, which Cody will tell you more about.
Drop foot, also known as foot drop, is a musculoskeletal issue that inhibits dorsiflexion or lifting of the foot. It causes a lot of issues while walking, causing tripping, slamming of the foot, and falling. It's caused by a variety of diseases, including MS, diabetes, and stroke. Because there's so many different things that cause it, there's a large number of people affected by it, and it creates a large opportunity for impact for a medical device to fix this.
To talk a bit more about the effects of drop foot, we're going to start through some gait cycles. If you're unfamiliar with the gait cycle, it's a process of how you take a step, broken into 5 different stages. On the top, you can see a typical gait cycle, which is what we're trying to get back to using footsies. Below that, you'll see the foot drop gait cycle. And if you focus on the second stage here, you can see that the foot isn't lifting off the ground, which can cause dragging on the ground, or you swinging your leg around and slamming the foot on the ground, both of which can lead to serious injury. On the bottom here, you can see the corrected gait using footsies. Again, just to show that the foot drop, it can lead to you dragging your foot on the ground or overcompensating on the side and tripping, falling, or other serious injuries. To step you through a bit more detail about what footsies does, we're going to step through the stages of the gait cycle. During the heel strike stage, distance sensors and accelerometers sense as you're moving towards the ground and know to drop the foot for the foot flat stage. During the mid-stand stage, the foot is stationary as your other foot is lifted off the ground and placed in front of it. During the toe-off stage, distance sensors and accelerometer again come into play as they sense you moving away from the ground and lift the foot from the mid-swing stage.
The gait cycle is a really great place to start with analysis of the foot and shoe. You can see here that if you break down the gait into different static parts, you can determine every force on the foot. We were able to determine a free body diagram with 1 degree of freedom because we were creating an orthotic instead of prosthetic. It made the initial calculations a bit simpler to determine the different forces and moments. From there, we were able to come up with specifications for our shoe that we were aiming for based on mobility, comfort, ease of use, and efficiency. From there, we were able to then go into our model to design our structural needs using finite element analysis, which Julie can tell you a bit more about.
So we developed this product in a very iterative way. This helped our mechanical and electrical sub-teams stay on the same page during integration, as well as give us a checkpoint for when we met with our advisors to show them what we're working on and what it was going to look like. As you can see here, our final project is going to be a 3D printed 3D model that can be fit to different standard US shoe sizes. And we think with more advanced manufacturing techniques and further iterations, we can reduce the overall height profile by 30 to 40% really easily. So Footsies is an integrated smart shoe and a paired activity tracker for foot drop patients to increase their daily mobility. How this works is that there are pin sensors located on the bottom of the sole that sense the distance from the ground. The custom PCB reads that signal, rotates the pulley, and lifts the cable, which allows the foot to clear the ground and the user to continue along his normal cycle, his or her normal cycle. So to follow those specifications that Cody mentioned, we needed a material manufacturing process that would fit our weight, our patient's weight, as well as protect the battery and other delicate components. So we're 3D printing in fiberglass reinforced nylon, which is a composite material 24 times stronger than typical 3D printed ABS plastic. This is made possible through 3D Hub's most recent continuous filament fabrication process. Allows us to fit all of our components into this custom midsole layer, which sits below the foot and above the sole. And this includes the motor, battery, sensors, and the custom PCB, which we designed to fit into the front toe portion of the shoe.
Because we're designing a biomedical device, we wanted to make sure that we're standing by certain industry standards, such as testing of the material, choose of rigid structural materials, and carrying and handling. We're also following IEEE wireless communication rules to make sure that we're abiding by the standards. And as of now, our product is standing under Class 1 FDA medical device, and we're also very careful about patient data privacy rules. As of now, we have the manufacturing cost of the $375 in total, and FootSees is coming in two products. Basic one is targeted for more standard design looking patients, and FootSees Couture is more for personal mapped and custom design patients. Currently, market competition is dominated by functional electrical stimulator, which is a device that sends electrical stimulation through sensors. And then it's followed by ankle-foot orthosis, which is a passive brace. And then it's followed by exoskeleton, which is not readily available for commercial purposes, but it's providing increased mobility. And FootSees is standing at a great position where it's providing the mobility, but at a relatively low cost. And because the market is growing exponentially, it's a great place to be. Thank you very much.
Here with Robin. We're Team 21, here to tell you guys about how we're going to make fencing more accessible to everyone. So the technology behind fencing hasn't really changed over the last 60 years. We're still using the same scoreboards and scoring system from the 1960s. These scoreboards and systems can be very expensive, up to $2,000 for each system. So if you're a fencing club that wants to start up, you have to buy a couple of these, and this is a very prohibitive cost for anyone wanting to get involved in the sport. The way it works also is you have wires connected to your back that connect to a wire reel that finally connects to the system. These wires can become a trip hazard during the fencing matches, since fencers can cross each other during the fight. What can happen is that the wires will disconnect and you have to stop the bout, or you can even break the wires. And the wires are owned by yourself, so you have to pay the cost of the wire breaking, even if the opponent breaks your own wire. And if you're a competitive fencer, you go through 3 or 4 wires every month. So you can see the cost starts adding up, making this a very prohibitive barrier to entry to the sport. The reason we do still use this system is because it's very reliable and accurate. So what we want to do is take fencing technology into the 21st century. We want to create a wireless solution that is both affordable and lightweight and can have the same accuracy and reliability of the current system. To do that, we've set a set of standards, specifications and constraints to allow us to reach that goal. Specifications regarding the validity of hits, so knowing when the hit has been on target and off target, hit discrimination, so knowing who is the first person to hit, and the certain rules that there are to fencing for simultaneous hits, as well as some physical and cost constraints to make the project affordable, which is one of our main goals, and compliance issues that will be discussed shortly by Robin. So there are 2 main design components to our system. The first one is the wireless transmission itself. We started off using Bluetooth Low Energy, or BLE, But the big problem with BLE is that it has a variable latency, and since we're working with 15 millisecond windows and very short time windows, this variable latency can be a huge problem to knowing who got the first hit. And it's also not secure. Bluetooth is very prone for interference, so it's not ideal for a competitive sport. The next iteration that we used was an I2C just to test the latency of a sub 1 gigahertz RF system. And we found we had got very positive results with the negligible latency through that, and which led us to the final design choice, which is the NRF95, which is one sub 1 gigahertz system on a chip that has negligible latency, is secure, and uses OpenThread to code. The second design component, major design component of our system is how do you know when the hit is valid? Fencers wear the lame, which is a wire mesh that Robin is wearing right now. It's very conductive, and that allows the fencing weapon to know when it's hitting the target or when it's not hitting the target. But once you take out the wires connected to the weapon and to the fencer, you take out the shared common ground of both fencers, making it very hard to distinguish between hitting on target and hitting off target. We thought that initially we could just run a voltage through the wire mesh and then have the fencing weapon find that voltage, but it's very hard to actually modulate, like find the specific voltage and get that working, so it's not very reliable. So the next idea was to create a common ground for both fencers by attaching a wristband to the weapon. That will create like a common ground. But the problem is that fencers wear shoes, and the shoes don't let them establish the common ground. And even if you could overcome the problem with the shoes, you're allowed to make hits while you're jumping, so that would also not work. So the final design choice that we had takes away the need for a common ground completely. It's just by redesigning the tip, which is a very easily removable part of the weapon, so it's not very intrusive to people that already have their equipment. And by two different hemispheres, one being positive, the other one being negative, with an insulator in the middle. And then once you actually hit the conductive material, so the lame, that will short circuit the system and you know exactly when it's been hit on target. I'll pass it off now to Robin so he can tell you guys a little bit more about the hardware and software aspect of it.
Thank you, Andre. So the fencing weapon is like one big switch. You have the tip at the end, and you have one wire per side of the switch running down the length of the weapon. Now, when a hit occurs, the tip is compressed, a connection is made to complete that circuit, and the scoreboard receives this and records this as a hit. Now the problem is all the wires that run from the fencer all the way to the scoreboard. In order to replicate this functionality wirelessly, we add the additional constraint that Andre just talked about to the tip. Now, in order for a hit to occur, the tip must be compressed, as well as in contact with the conductive material, which what I'm wearing is. And this is the target area for fencing. This is where the hits count, on the lame itself. Now the hit is registered by the Weibo device at the hilt of the weapon, and the Weibo device sends the ID to the scoreboard, which then displays the proper output. This is the key component to our system, so no more wires. The scoreboard itself does the computing. Excuse me, this is very tight. It receives the ID from the Weibo device, as well as the timestamp at which it receives that signal. It then loops through a set of logical outcomes until the first match occurs, and it displays this as a score. Now the communication between the Weibo devices and the scoreboard takes place at a sub 1 gigahertz frequency. In order to abide by the IEEE standards that apply to this, we use OpenThread, which is a networking protocol that's used for low-power personal area networks. It was created by a company called Nest, which I'm sure some of you guys are aware of. And, another constraint that we must consider is the max 15 millisecond delay or latency in the communication. Now this is necessary because fencing is a very fast-paced sport. Simultaneous hits by fencing standards are allowed if they occur within 50 milliseconds of each other. Now the hits must maintain contact with the opponent's lame for 15 milliseconds. This is where we get our latency requirement from. Now the design required the development of a new tip, casing, as well as the communication software development and the powering of the Weibo device. Andre has experience with mechanical engineering, so he was able to do the machine and 3D printing for the tip and the casing. I have a background in microcontroller development as well, so we were able to split up the time. We were a two-person team, so we ended up doing a lot of this together. And finally, this is how much everything costs. I'd just like to note that we're staying within our goal of being an affordable alternative to the current wiring system. Thank you, guys.
Hi, I'm John, this is Yoni, Chris, and Angelina, and we are Communicate. Along with our advisor, Professor Firouz Aflatuni, we sought to create a wireless 60 gigahertz communication system able to operate at high frequencies and send large amounts of data. So 60 gigahertz is an incredibly high frequency V-band wave with an incredibly small wavelength, around 5 millimeters. This allows for incredibly high bit rates. You're able to send more data more quickly in a shorter amount of time. In addition, because the wavelength is so small, the antenna is incredibly small, allowing the entire communication system to fit in the palm of your hand. Finally, the entire waveband from 57 gigahertz to 64 gigahertz is unlicensed and unregulated internationally. So we can use this without any problems and have an uncongested wavelength, an uncongested band, so we can send large amounts of data without any problems. We saw massive potential for this because it can be scaled into homes to send data from a computer to a TV or in a very condensed metropolitan area.
So for our project, we wanted data transfer speeds to be nominally around 1 gigabits per second, which is a bit optimistic, but we wanted to go for that. Over a distance of at least a centimeter and a total power consumption of less than 1 watt. Due to the short wavelength of the system, we had to make sure and manage all the transmission lines that are inherent to the board in the system. Ultimately, we decided to go with a standard transceiver design, so we input a signal into the transmitter board, whereby it's amplified and modulated, and it's sent to the receiver via an antenna. There, it's amplified again and demodulated before it's ready to be used. So, since our design overall is fairly standard, we didn't really have any large modifications to our project. We did, however, look at different antenna designs and high-frequency board material before settling on a patch array antenna and Rogers 4003 material.
Our transmitter takes in a low-frequency signal and then converts it using the HMC 6300 chips on board, and then sends it through an antenna to the receiver. Because our output for the chip is differential, we had to bind it into single-ended using a rat race coupler designed on board. And because of the 60 gigahertz frequency being such a small wavelength, our boards end up being very small, less than 3 square inches.
Yeah, so our receiver board basically does the opposite of the antenna. It receives the signal via, of the transmitter. It receives the signal via an antenna and sends it into an HMC 6301. The input signal is going to be single-ended, but the output signal is going to be differential. Unlike the transmitter, we don't actually need a coupler. We can put this differential output directly into an oscilloscope for viewing. As with the transmitter, the board's incredibly small. It's about 1.5 inches by 1.5 inches for about under 3 square inches as well.
So at its core, the transmission system relies on an antenna to be able to transmit data from the transmitter to the receiver. An antenna is basically just a conductor that is perfectly shaped and has the perfect size in order to receive or send electromagnetic waves at a specific frequency. So our patch array antenna, as you can see in the picture, was specifically designed for operation at 60 gigahertz, so it can induce a voltage or a current or react to a voltage or current at 60 gigahertz. The images around the antenna design show the simulation and performance of our antenna. So the top image is a simulation, it shows the isotropic nature of the antenna. It can transmit data and receive data in all directions of equal magnitude. And the bottom one shows its return loss, showing good return loss of negative 10 dB at our frequency of interest, 60 gigahertz. So in terms of project management, how we divided roles, we decided to divide roles based on our past experiences and what we had done before. So I have antenna experience. I worked on antenna design. Angelina has done a lot of work with RF research and also PCB work, so she worked on the transmitter and receiver, whereas John and Chris worked on deliverables, making sure we were on schedule. And then ultimately our entire team worked together to compile the project and to test it.
So we worked with some fairly complex components, and so we had to follow what the industry standards are for these. Now we used a 0.5 millimeter ball grid array for the HMC 6300 and 6301. That's incredibly small, so essentially it's these tiny balls that go on the chip, and from center to center ball is 0.5 millimeter. So we had to follow the standards that Texas Instruments and Xilinx set up for this, and make sure that every PCB manufacturer we talked to was able to comply with this. In addition, RF PCBs have to follow slightly different guidelines to make sure transmission lines don't form. So we had to follow what Texas Instruments and Analog Technologies recommend using. In addition, Rogers Corporation create Rogers boards that use these high frequencies, have standard thicknesses for the laminates that we use, so we had to follow their outlines as well. As far as other things go, IEEE has standards set out for antenna testing that Yoni and Professor Aflatuni and the different PhD students that we worked with used as we tested our antennas throughout the process. In addition, IEEE added 802.11ad, which is an extension of 802.11, which is the wireless Wi-Fi standard, and this is the Wireless Gigabit Alliance, or WiGig. It basically outlines how you use 60 gigahertz and the range from 30 gigahertz up to 60 gigahertz, and includes that unlicensed band from 57 to 64 gigahertz. Finally, if we were to scale this project up and to add different things that I mentioned earlier, whether at-home use or large metropolitan area use, IEEE has a list of standards on their website in a database that lists those types of things like metropolitan use, home use, wave propagation, and even more. Finally, this is our bill of materials. So things were fairly expensive. We spent about $3,000. The majority of that cost just came from parts. Because 60 gigahertz is fairly novel, very few companies are doing it. It's mostly just a form of research at most institutions and companies, and only really being used by the military at the moment. For that reason, parts are incredibly expensive. The antenna adapters, just to test and use our antennas, were just under $500 each. In addition, board costs were incredibly expensive because only a few companies can make it, and they have to use those Roger boards, which are not cheap. So the boards came out to around $2,000. It's important to note that whether we created one board or 32 boards, which we ended up doing because that's what they would do at max, it was the same cost. It was going to be $2,000 just because that Rogers material was that expensive. In addition, that $3,000 does not come into effect the things we got for free. So we received over $3,000 in free materials from Analog Devices and from Rogers. So that's our presentation. Thank you so much.
Hi everyone, I'm Philip. I'm here with Allison, Rihanna, Enrique, and Bill, and we are Team 20 Balance. So, meet Evan. Evan's the owner of Elixir Coffee, which is a world-renowned coffee shop in Philadelphia that has world-class baristas. Those baristas are focused on the important things, like the customer and also the coffee. So, sometimes they miss the minutiae of bill handling. This results in Evan losing approximately $10 to $20 per day in the 60% of transactions that are cash. So what Evan needs is a system so that his cashiers can connect with the customer without having to worry about the bills.
So business owners like Evan face the problem of losing money while cashiers are fumbling with bills and need to do quick mental math.
Therefore, we're proposing an electromechanical device that counts and dispenses change in real time, while still maintaining the human-centric role of the cashier.
In the spirit of our interdisciplinary team, we've offered an interdisciplinary solution. Meet Alan.
Let's go through the design flow of Alan. For example, a customer buys a $4 latte and pays with a $5 bill. The cashier loads the bill in the appropriate denomination slot and hits pay. Alan then counts the bills, recognizes that change needs to be dispensed, and dispenses a $1 bill in the appropriate slot. The cashier receives purchase verification, retrieves the bill, and gives the change to the customer.
So this brings us to how the internals of Alan actually work. We call this the ABCs of balance. A is where bills are acquired by the cashier and put into the register. B is what we're calling the bank section, where notes are stored. And then C is where the change is dispensed to be retrieved. In order to get this whole flow working, we needed to master how to move paper money. We started out with a horizontal configuration, most similar to a traditional cash drawer, but found moving the bills from this place were challenging because it was both slow and pretty inaccurate. So we were inspired by a compact bill counter that we studied and oriented the bills vertically. This was successful in moving the bills individually, but the motion tended to be chaotic as bills were being flown upwards. So we reoriented it and let gravity guide the bills down. And as the bills were being fed downwards, we refined how they were caught and got things in a much more orderly way to be contained within our system, and then expanded that to have an A, B, and C compartment.
Our final iteration is Alan, a seamless A to B to C device that counts the input bills, stores them in a central bank, and dispenses them on demand directly to the customer. Alan features two DC motor subassemblies that actuate a tapered elastomeric wheel at the corner of each bill, ensuring individual bill separation along an angled path. We are using a geometrically elastic thin material as our input to bank director that still allows for deflection for dispensing of the bills. We are also using an angled shelving system that takes advantage of gravity to help mitigate against the challenges of bill dynamics. One of the goals of our designs was to help prevent cash discrepancies that occur through human bill handling. In order to do this, we implemented a servo-actuated door that automatically dispenses change to the customer without human interference. Lastly, I'd like to emphasize the modularity of our system, both in the motor subassemblies and the counting compartments themselves, allowing for ease, manufacturability, and assembly.
I'd like to talk a little bit about the embedded system. So how the bills are actually counted is that as the tapered wheel moves the bill between the motor and the back plate, it interrupts an infrared LED phototransistor pair, which creates a voltage drop that can be detected by the embedded system. So this is also the same embedded system that's communicating the point of sale to do the calculations for how much money should be coming into and going out of the system.
Looking at the software iterations, our initial and ultimately ideal solution would be for the cashier to be using a third-party application like Clover or Square, which sends the transactions to the Arduino powering our system, as well as sending the data to a database which would be queried by our client application. However, due to the prototyping nature of our solution, we decided to implement our own point-of-sale application, which sends the data to the Arduino as well as a Firebase real-time database to be queried by our application. Here are some simple screenshots of our point-of-sale application with purchase verification for the cashier, as well as our client application with a simple login and traditional analytics such as cash flow and transaction frequency, as well as drawer status.
Like with any good design challenge comes a set of design constraints. It is imperative that we keep our mechanical workflow within 7 seconds, a standard and benchmark that we establish by observing real cashiers during our user testing. There are cash drawer standards that we adhere to, as well as standards set forth by IEEE for Wi-Fi and Ethernet. There are also physical constraints such as space limitation, power consumption, and variability in the input bills.
So every step of the way, we were conscious of industry standards as well as ethics. Unified POS offers a set of standards that they recommend, many of which we expose through our API, our database, as well as our POS application. In addition, we have a set of ethical considerations that our entire team adheres to. So Balance, our system, is here to keep everyone honest, the consumer, the retailer, as well as the employees. So by pushing transaction data to a remote database, as well as logging the information on our embedded system, a practice that is inspired by Google Cloud's Big Table white paper, we're able to track transaction data redundant against failures. So when doing market research, we were quick to observe that our product situates in a part of market that is traditionally known to have little innovation. So instead of mandating external standards or demanding high price premiums, we offer a low-cost integrative solution that is both visual as well as user experience appealing, and that works right away as soon as we put it in.
So looking to the future, we'd like to test this with Evan at Elixir. Also hone our solution into a product, making a few corrections and also optimizing for space. Thank you for your time.
Hello everyone. Our project is deep learning models for alternative splicing. I'm Nazir, this is Liam, this is Joe. Right, so our project is a mix of genomics and deep learning. So basically my background is in the process of gene expression, which is when the information contained in DNA is decoded by the body to instruct protein synthesis. DNA is copied into an intermediary compound called RNA, which is then copied into DNA. This first process is called transcription, and then RNA is translated into protein. So in this phase where the information is in RNA, certain important parts are kept by the body and unimportant parts are spliced out. This process is called splicing. So sometimes splicing can be misregulated, and this leads to many diseases. So sometimes certain important parts of RNA are thrown out by the body or spliced out instead of being kept in. So the problem that we're trying to solve is that we're trying to build a splicing code. What this is it is a mathematical model or a computational model to explain the process by which genes are spliced. And the goal of a splicing code is to predict which proteins will be synthesized in the body based only on genetic information. So past models have been able to predict this very well. Our lab has worked on probabilistic graphical models and deep learning models, so deep neural networks. The step here, our next step, is to develop a new model to try and improve the accuracy of our predictions.
So the class of algorithms we looked at were convolutional neural networks. So two features there. First is convolutions. So I think the most common example that convolutions are used in is image processing. So say you want to learn things like where the border on a picture is, or how to recognize circles within a picture. You use filters and you convolve them with the image, and the output gives that kind of idea. Here, we don't know what the filters are ahead of time. They're not deterministic. We want to learn them through this process, and that's where the neural network comes in. So how do you view DNA as an image? Well, we view it, instead of as a two-dimensional image with 3 channels for red, green, and blue, we view it as a one-dimensional image with 6 channels. So the first 4 channels encode the nucleotides. One channel encodes free energy, so how likely it is that a spliceosome will bind to a given nucleotide, and therefore how likely it is that that sequence will be included or excluded, and finally conservation, so how common a given sequence is across species. And with that data, we input it into the network, we pass it through our convolutional operator, and then we do pooling. So pooling is a form of dimensionality reduction that helps protect against overfitting. We do that process again, and then we pass the output of that to a dense layer. So that's just kind of a classic neural network architecture. And we learn three things: the raw percentage inclusion of a given exon, and then differential inclusion. So you might expect that, you know, for some proteins you want that to be synthesized more often in brain than you would in liver, and so there's a real differential there that we want to train this model against. With respect to standards, since it is a bioinformatics project, we looked at two different types of standards. The first is software standards. So IEEE puts out things about best practices, and we used version control software. We wrote on different branches for testing and then merging when we validated our tests. And then with respect to the health standards, we looked at three standard setting bodies. So IACUC at Penn focuses on the collection of data, and our data is from a major Nature paper by Keen et al. In 2011, and so as long as we're compliant there, we felt comfortable. If we're applying the model to humans one day, IRB will require data anonymization. We don't even have identifier fields in our data right now, so also comfortable there. And then the last one was HIPAA. And we just want to make sure that in the future our data providers are HIPAA compliant as well.
And then the main cost of the project were using GPUs, which are speeding up the computations for these big networks. And we borrowed those from the lab that we're working with, and they let us log on remotely. And so there was no cost incurred there, and then all of our software that we're using was open source. And I'll talk a little bit about how we use that to try to get this model to work. So when you're training a neural network, you feed your data forward and then try to reduce the training error by adjusting the parameters backward. And across this process, our training error was not decreasing. And so we employed a few techniques to try to get that training error to decrease across feed forward and feed backward. The first thing that we did was we looked at the hyperparameters of the problem. There are about 20 hyperparameters governing our model. These are just things that tell us about the overall model architecture, how many nodes in the dense layer, how many filters in the convolutional layer. And it's a huge space. And so we guided that using Bayesian hyperparameter search, using an open source tool built by MIT researchers to try to make sure that we're in the right search space. The next thing that we did was we incorporated past knowledge into the model. We got probability matrices from the researchers that we were working with of where the past models had said these features are significant. And we initialized our filters at those spots to try to get them learning in the right place initially. The next thing that we tried was different normalization schema. We mean centered, we standard deviation scaled. We did this across the data set and across images, and also tried stretching the images, because sometimes these can help pull out signal from the data. And the final thing that we did was we built a pipeline to visualize the filters on our model, because these models are very hard to interpret. And hopefully if we can relate it to the biological significance of DNA sequences, then we can actually figure out if our models are learning anything. By the conclusion of these steps, we had thought there are two options. Perhaps a convolutional neural network is not a model that can be used as a splicing code, or perhaps further iteration through techniques such as these could be used to try to extract data from, or extract signal from the data and get this model to work. Thank you.
Team 14, and our project is Yelp with an H, and we're going to talk about how we redefine the way that you review businesses. In this specific case, we specifically did Yelp because that's what we had data for. Our advisor is Dr. Victor Cresciato, and we also had help from his PhD student, Jorge Vergara. So the first thing we want to talk about is why does Yelp need help? Well, there's actually a lot of research online about just a lot of problems with Yelp. You know, it ranges from anonymous reviews being unfairly biased towards the negative, and this especially hurts small businesses. And then, anyone can sign up for Yelp, and there's no qualifications needed. And really, everyone's opinion is weighted equally, and it's really all subjective. And people really take these subjective reviews seriously. So for our project, these are objectives, specifications, and constraints. In addition to looking at how we can better re-weight Yelp reviews overall, we also wanted to see if we could help these small businesses that are especially being hurt by the review process. In terms of specifications, we wanted our project to be as objective as possible, and we also wanted to be able to validate what we're going to do, and we want to be able to present our data clearly. And then for our constraints, we had some limited data, and we also had limited computing power. Okay, and then in terms of standards, the main one we want to focus on here is the Yelp dataset license. This prevented us from sharing too many of our findings too publicly, so we'll show you a website that we mocked up, but we weren't allowed to publish it at this point. And next I'll hand it off to Connie to talk more about some of the Yelp dataset.
Thanks, Albert. So here you can see some of the characteristics of the dataset we were working with, and as you can see, the dataset was rather large. However, we were limited to targeting specific regions of the US and Canada. We did pursue a few alternative designs, such as the checks and balances approach, and an approach where we were going to aggregate these scores and find an average. However, ultimately, we decided that both these approaches were overly subjective, so we wanted to come up with a more objective measure. And so, our overall system design has three components: trust score, validation, and demonstration. The first step was to calculate a user's trustability score and use these scores to re-weight the original Yelp ratings and to create our new ratings. Then we wanted to validate whether it was reasonable for us to penalize users who had a lower trust score. And so we used various text analysis features to do this. And finally, we demonstrated our findings on a website. And here's a little bit of an overview of how we split up the work among our team members and our advisors. And now I'll pass it on to Sean to talk to you about what this trustability score is.
Thanks, Connie. As Albert mentioned before, we had two objectives for this project. First was to find a way to re-weight or to weight reviews on Yelp, and the second was to find underrated small businesses. And to achieve that, we had to use our trust scores to adjust for each business rating. First, we calculated the trust score for each user, then assigned higher weights to trusted users, and then re-weighted each business's reviews to calculate a new average. And computationally, we achieved this by first looking at the user. We took the average rating of a business, and then found the bias for each review, which was the difference between that review's rating and the average rating. We then found the standard deviation of those biases for all users. And then second, we looked at each business. We took those standard deviations and normalized them for each review to find how much weight a review would have on a business. And then we updated the average rating for each business using those weights. Next, I'll pass it off to Joyce to talk about validating our findings.
So the purpose of our validation process is to answer one big question. Does it make sense for our system to penalize users with lower trust scores? So our preliminary process involved just simply manually reading through the reviews of each business. However, as you expect, this is highly inefficient and involves a lot of time on our end. So we came up with a better solution. What is the solution? We're going to automate reading through the reviews and use text analysis to determine the quality of the reviews of each user. So here's a brief summary of the results that we managed to obtain. So for our classifier, we created a new response variable that basically assigns a value of 1 to the top 5% trusted users based on our trust scores. All the users that fall outside of that range will get assigned a value of 0. So we have a binary classification. We use 6 text analysis predictors, as you can see here. And finally, as a statistical metrics that we obtained an area under the curve of 0.789. So to give you some context to this number, area under the curve values range from 0.5 to 1. 0.5 signifying a meaningless test and 1 signifying a perfect test. So in other words, our classifier can correctly separate trusted Yelp users from non-trusted Yelp users with an accuracy of roughly 79%. So please enjoy the demo video that we have prepared that shows you the website we created to display all of our results.
Here is the homepage of our Yelp website. It shows all the tabs and pages that we created. The next page is our vision. We demonstrate why does Yelp need help with some quotes that we have, as well as an overview of our design and some specifications. We also include industry standards.
You guys can speak.
You can just talk us through it.
So that tab was in our vision and overview of our project. So this is our solution. So it kind of walks you through what we talked about in the presentation, and it shows you some of the tables that we have on MySQL. This is a validating our findings page. So this is like the nitty-gritty of what we did. The text analysis feature is how we validated our results. And here's just some code to kind of demonstrate what we were working on. And this is the final results ROC curve that we showed you in our presentation. And then finally, this is the Browse Businesses tab. So here, you can choose a city from this drop-down, such as Phoenix. You can search, and then here, it'll show you the original Yelp rating, and then our rating that we re-weighted the ratings to become. So here you can see that a lot of these businesses are very underrated, and we think that they do deserve a higher rating than they actually did. And you can see their addresses, review count, and what city they're in. And this is a simple contact page, a little bit of information about each of our team members.
That's everything. Thank you.
Thank you.
We're good? You're good? Alright. Hello everyone, I'm Julian, this is Cameron and Leah, and over the past 9 months we've worked on an app that we're calling Plexus. The idea behind Plexus is to democratize financial algorithms for the general public, and today we're going to show you what we've done over the past 9 months. To start, we wanted to think about a problem that we wanted to address. All three of us are interested in financial markets. Cam and Leah are working for 2 financial companies after graduation, and I'm just generally interested. One thing we noticed is that algorithms, especially academically backed algorithms, are really coveted and covered by hedge funds and investment firms and not available to the general public for understanding. So we wanted to kind of try and solve this problem. All of us are interested in graph theory as systems engineers and computer scientists, so this is an emerging field that we wanted to explore as well. And finally, we're all pretty big into data science as this emerging field becomes important in our world today. Thus, we ended up creating Plexus, which is a web application that looks to create a network of the S&P 500 stocks in order to determine relationships so that the general public can make better investing decisions. So just to go over a couple of our alternative designs and road bumps that we ran into over the course of the semester. Some things were the access to real-time data. As you can imagine, stock data is pretty heavily regulated, so it's not always easy to get that in real time. Computing power generally was just an issue. We're tracing back over 30 years of daily stock data, so we had to store this on Amazon's EC2 server. Additionally, just ability to compare with other algorithms. So we were working within kind of our own frame of reference because you can't have access to what other algorithms are doing. So some of the other considerations that we had over the course of the semester was the type of correlations we were using amongst stocks, which is mostly mathematical, looking at different types of regressions to help with our transformations, and finally determining how frequently we were going to update our network to provide information to users. So to start the process, just to walk through a bit of our data collection, we started with a weekly poll from Bloomberg data. This helps us get a lot of stock information. We bring this into a Python backend where we analyze and clean the data, and then we are also overlaying this on the signal during that time. And then weekly updates now that we're pulling from Quandl in order to get just live time stock data. We use that because it's free and it's easier to just integrate with our system. So Leah's going to talk a little bit more about the algorithm and where we progress from there.
Yeah, so Julian mentioned the general idea of our algorithm. So it starts with taking a time series historical data of all the stocks that we want to look at, in this case, the 505 stocks of the S&P 500. So an example here would be Apple and Microsoft. They have this type of time series data, which we take it as the percent change in daily pricing. And then we run a correlation on all of these points and put that into our network. So if you have this correlation between Apple and Microsoft, that is the edge between Apple and Microsoft in our network, where the nodes are the stocks and the edges are these weights. And so once we have our network, as Julian mentioned, we want to overlay our signal on top of this network. So our signal would be, if you are a user and you go onto our website today, we are going to pull all of the percent change in prices of all the stocks that we are including from our network as percent change price, and then we're going to overlay that on our network. So an example here would be if you're pulling these stocks and you're showing the arrows or the percent change in price of the current nodes, so for example Amazon, Microsoft, and Apple, and the underlying network has red connections for a negative relationship. So we then look at the graph Fourier transform of this, which would be looking at low and high frequencies. So in this case, what low means is that if you have Amazon and Microsoft, they have opposite signals and they're connected by a negative weight. So that would be in line with the network because they're expected to be different ranges of pricing. Whereas Microsoft and Apple have positive signals, but they're connected by a negative weight as well. So that would be considered high frequency on the network because the network says that they should be having different prices, but they currently are aligned. And using these different frequency notations, we then can determine whether or not a stock is expected to change in price in the next day or week. So for example, one of these, depending on the other connections within the network, would be expected to change soon because it's not defined. And now Cameron will go over our actual AI.
Thank you. So as Leah and Julian stated, the crux of our project is really the algorithm, but this means nothing to a user without a way to see it. So we've created a user-accessible web app for them to view. These are two of the main pages. The top one is the home page, which shows our top predicted stocks are both increasing and decreasing on a given day, so that any user can get immediate ideas of where they might want to look in the algorithm. Next, not shown, there's a search bar that would lead, or you can click any of these links to the particular stock page, which gives information about the stock, such as the price. It gives a time series graph of the price over the past week or so, and it tells you what our algorithm says it's expected to do, increase, decrease, or if we don't think it's going to change significantly. Additionally, we give our historical accuracy for predicting that stock because we predict stocks with varying levels of accuracy. So people who are more risk adverse might lend themselves to really wanting to take our advice for the stocks with high percentages such as 76 or 80%, and not the ones with slightly lower. Additionally, we have other pages that give information about how to use the site, information about the team, and then because we want to give full transparency to the users, a general idea of how our algorithm works, which is basically what Leah just described. And then also we have a stats page displaying our general strategy for a strategy for investment and how our quote-unquote portfolio performs. And this is all a single-page web application made with React and a Python backend hosted on Amazon EC2 server. And now finally, Julian's going to tell us.
Just to wrap up, a couple of things that we considered throughout this project were just our general compliance standards and things that we had to make sure we were aware of throughout this process, and we divided these into 3 categories revolving around data, finance, and kind of our ethical considerations. So on the data end, we had to be sure that we were complying with any sort of data standards, making sure we were using correct data sources and using it in an honorable way. Additionally, from the financial end, this mostly revolved around using correct financial terms, not portraying that we are an advisor, that we are instead just an informational tool and not looking to provide investment advice to users. And finally, just from an ethics end, there's information out there about algorithmic bias and making sure that you are not presenting, say, stocks that we have, investments in and portraying those as the wisest decision. And that's really it. That's Plexus, and you can come explore in the demo. Thank you.
Alrighty, first and foremost, thank you guys for being here today. We appreciate all of your commitment and support to the curriculum here at Penn. My name is Danny Clyde. I am a bioengineer, and I'm joined by Michael Ramdat, who is a systems engineer, George Yuan, who is a computer scientist, and Shiv Dalla, who is also a bioengineer. So we are an interdisciplinary team tackling the problem of vaginal dilation. So we were approached by a multitude of CHOP clinicians who had discussed the problem of vaginal dilation as it pertains to transgender patients. Specifically that transgender patients after undergoing gender reassignment surgery require dilation therapy 5 times a day, up to about 30 to 45 minutes per session. The problem with that is it's extremely painful and it's extremely time consuming. And so a lot of patients who use the standard rigid hard body dilator right now find it to be extremely difficult to comply with their dilation therapy. And as such, every single patient who has undergone gender reassignment surgery within the Penn and CHOP health clinics have required revision surgery, which is extremely expensive. It can cost upward of $20,000, not including any kind of hospital stay or anything like that. On the other side of the equation, we have patients who are born biologically female who have a multitude of issues, including MRKH, which is vaginal hypoplasia, or a lack of development or underdevelopment of the vagina. Patients who have radiation therapy in the pelvic region, who form fibronic tissue who require vaginal dilation to improve the elasticity of the vagina. And also patients who have vaginismus, which is essentially painful insertion of anything into the vagina. And this also does not include patients with dyspareunia who have any type of painful sex or painful intercourse. And so these patients on the left, or it's your right, don't require as much dilation therapy, but it's definitely a market that we're interested in and would hope to be able to corner at some point. So now Michael's going to talk a little bit about how we've decided to improve the dilation process.
Thank you, Danny. We use a variety of sources to develop our solution. Knowing nothing, we first walked in and did some independent research to figure out what are the conditions we're really looking at here, what are the generally accepted treatment plans, and kind of what are the currently existing dilator offerings in the market. Next, we talked to a lot of physicians. Our advisory board is made up of many physicians, including the directors of the CHOP Gender Clinic, 2 of the top gender reassignment surgeons in the country, and an OBGYN. And this gives us a full spectrum of expert coverage over all the conditions that we're looking at. And finally, and most importantly, we talked to patients. If you didn't get a chance to look at our video yet, a patient's story was really the influence for this project in the first place. And so it was really great that we got to actually sit in on patient post-op consultations with our surgeon, one of our surgeons on our advisory board, and actually hear directly from them, see them the first time that they're using dilators, and hear kind of like their feedback of why is this painful, why is it uncomfortable, and what are the challenges with being compliant with the treatment plan. From day one, our primary goal was to deliver a dilator tool that eased pain. And so our first priority was, can we create an electromechanical dilator that inflates, uses a balloon mechanism that will serve male to female transition patients and also those with vaginismus. Our stretch goals focus on using data to address the compliance issues that Danny raised a little bit ago. So our second priority was, can we capture device data and link it to an external device? And third, if we had time during the semester, could we develop a patient app that actually allowed patients to give feedback and develop a remotely accessible physician portal that offered valuable insights on the treatment plan. And we're proud to say that our spring prototype achieves many of our initial goals. So we have an electromechanical balloon dilator that you'll see later on today. It has a UI that allows a patient to control the settings. It's capable of delivering 6 psi of dilation force. It has a 12-hour battery life and software and hardware safety mechanisms. And as Shiv will talk about in a second, it does feature wireless data communication.
Thank you, Michael. So right here is a little diagram, block diagram of our device. You can see on the far left side our non-compliant balloon. On the right side, the pump, which inflates the balloon, and the solenoid release valve, which deflates the balloon as needed. There's also an emergency release valve, so if the patient feels uncomfortable or unsafe at any point in time, they can simply flip that switch. It'll completely disable the dilation device. This is all interfaced with my controller, which controls both the air pump and the release valve. To power our device, we use a 3.7 volt LiPo, relatively small and cheap, been used in a lot of devices before. For our sort of the heart of our device, we chose to use the ESE32 microcontroller, which is a low power consumption controller, and it has built-in Wi-Fi and Bluetooth, so it allows us to transmit data, as Ramdat mentioned. It's also relatively cheap. For the air pump, we use ones that are similar to those used in blood pressure monitors, the ones that are on the wrist. It's relatively small, cheap, and it's already been approved for medical device usage, so we thought, why not try one of those? Similarly with the solenoid, been approved, been used in previous medical devices, so we just decided to go with that. The pressure sensor is a small, accurate pressure sensor, just an integrated circuit that we mount on our board, $7. And the most expensive thing actually on our list is the OLED monitor, which is about $20. It's got good resolution and allows us to display all the information we want to the patient and allows them to control everything they need to. George's going to talk a little bit, the next slide. In order to give all the data to the patient, we have been uploading it to ThinkSpeak, sort of as a proof of concept. We have tracked the patient data as well as a serial number for the device, and that gets uploaded to ThinkSpeak, and then we can then visualize it. You can see that in the demo later. Dora's going to talk a little bit about the team.
Thanks, Shiv. So Danny alluded to this at the start of the presentation, but we're a very interdisciplinary team spanning across 3 different departments within the School of Engineering. First we have Shiv, who's largely responsible, who led the hardware design, as well as CAD efforts and prototyping our product. Then next we have Danny, who led most of the bioware design and was the lead on information about how we're going to develop the actual dilation part of our device. Next we have Michael, who was our key point of contact for our many stakeholders and advisors who helped us out graciously throughout this process. And everyone on the team assisted with the hardware design. And lastly, I myself was responsible for the software and application elements of our product. So this is a list of our budget and costs and parts. The main thing to notice is that our product is relatively cheap compared to, first and foremost, what's available on the market today, hard rigid dilators, and second of all, revision surgery, which often is extremely expensive and many people have to undergo today. The key thing to note about our spray expenses is that the non-compliant balloon, we managed to receive one for free, so that cut down greatly on our costs. So as a medical device, as you can imagine, our device has a lot of standards and regulations that we have to comply with. First and foremost, the FDA. The clinical trial process for our device is much simpler than it would be for a novel device because this is an approved process and there are already devices and products on the market that achieve dilation therapy today. So it's going to be a lot more simple for us. In terms of the actual electronic and software components of our device, there are also standards that we have to adhere to, primarily in the realms of data transmission, which are areas that we're looking at, and other standards are going to mostly be dealt with by manufacturers and our suppliers. Thank you for listening.
facilities servicing low-income patients face incredibly high no-show rates. Missed appointments cost the U.S. healthcare system about $150 billion each year. This is an incredibly complex issue with many contributing factors, and because of this, it's often hard to identify exactly which factor may be affecting a given patient. Our team has decided to look at transportation. Transportation to primary care is a huge obstacle for patients that are covered with Medicaid. According to the National Academy of Sciences, about 3.6 million patients miss appointments each year due to transportation barriers. That's where Predicare comes in. I'm Barry, and I'm here today with Claire, Sonia, and Sabrina, and we have built a predictive algorithm to identify which patients would benefit from individualized transportation scheduled by a social worker, also known as transportation intervention. Because of the complexity of this issue, we had to go through numerous iterations and speak to many stakeholders before coming up with the design that we have today. Some of these alternative designs included optimizing booking and potential for overbooking, as well as looking at the actual transportation systems that these patients are currently using to get to their appointments. This all led us to our final design. Our design has three main objectives: get patients to their appointments on time, identify patients who would benefit from transportation intervention, and assist social workers in scheduling patient transportation. The design specifications is our data set. Our data comes from a controlled clinical study done by one of the primary care clinics here at Penn, and includes demographic and behavioral data, as well as transportation and attendance history. I'm now going to pass it off to Sonia, who's going to talk a bit more about our design and our algorithm.
Thanks, Barry. So after collecting our data, we began gathering input from various subject matter experts, including doctors, social workers, professors, and researchers, both from the transportation and healthcare industries. There are so many different ways to approach the objective of getting people to their doctor's appointments, as it is such a complex problem. Therefore, these stakeholders were invaluable in helping us decide what questions we should ask of our data during the analysis phase. They also help us decide what the ultimate output of our algorithm should be. In this case, it's a recommendation of whether or not a given individual is likely to benefit from transportation intervention. That algorithm output is then incorporated into our prototype website, which is accessible by our end user, which is a social worker. They're able to view their patients' profiles as well as the algorithm recommendation in order to make a final decision of whether or not to offer and schedule transportation assistance for an individual. Now to delve a little deeper into our algorithm. We began by isolating our target population, which was those who had missed appointments in the past, but had the potential to benefit from transportation assistance. We then looked at characteristics that differentiated those who did and did not accept transportation intervention in the past, and used those to perform unsupervised clustering as well as supervised regression analyses in order to provide a final recommendation. Our final algorithm has a 9% false positive rate on high prediction profiles, high priority predictions, and a 30% false negative rate on low priority predictions. And overall, we're really happy with this because our goal was to minimize the false positive rate in order to not waste clinic resources scheduling appointments that were unnecessary. Further, we said that the aim of our project was not to give a finite decision of whether or not a given individual would definitely make it to their appointment with transportation intervention. Rather, the goal was to provide a device for social workers in assisting them in better understanding their patients and therefore making a more informed decision of whether to use clinic resources and helping a patient get to their appointment. I'll now pass things off to Claire to discuss our prototype.
Thanks, Sonia. For our next step in the design process, we built a prototype so that the social worker can actually use the results from our algorithm. We used Just in Mind, a prototyping tool that allowed us to create realistic and data-driven prototype. This became very crucial in getting reliable feedback during UX and UI testing. Due to data privacy restrictions, we could not create a fully integrated app with Epic, the standard clinical patient management system. However, we are creating a full report of all technical specifications, including HTML code, so those with access to Epic can fully build this out. Now let me walk you through two of the main screens in our prototype. After securely logging in, the social worker is directed to the home page, as shown on the left. This lists all patients in order of their next appointment date, with filters available on name and priority level. On clicking on a patient, it opens up their profile as shown on the right. This shows information pulled from Epic. This is fixed information that the social worker can't edit. This includes previous visit information, as well as other editable fields, such as the notes field and the priority level, which are two of the most crucial ones for the social worker. The notes field is pretty much where the social worker lives and puts all information that they can't find elsewhere. And the priority level is the direct output from our algorithm. This categorizes patients as high, medium, or low priority, so the social worker has an idea of whether that patient will benefit from transportation intervention. Finally, we also have a glossary of different patient profiles for the social worker to reference and get a better understanding of our data right in the app. Now I'll pass it off to Sabrina.
Thank you, Claire. So as Claire mentioned, our prototype includes a feature so that social workers can override a patient priority status on a patient-by-patient basis. And this is a direct outcome of the algorithmic bias consideration standard. This standard requires that we are aware of how the algorithm may influence an end user so as to avoid unjustified differential impact on patients. So how does this influence our design? Our design is not an end-all be-all, but rather our algorithm is part of a larger human system, where at times human input is required to override our outputs and make final decisions on a patient basis. Over the course of the 2 semesters, Claire worked on the prototype design in Just in Mind, and Sonia was primarily responsible for the build-out of the algorithm in R, and Barry and I were responsible for gathering requirements across various task areas. Testing medical interventions is very complicated. During our design process, we are specifically challenged by the complex nature of low-income populations. There are many unobservable factors that drive these patients' decision-making, their behaviors, their choices. With that said, our aim was never to solve the entire problem regarding healthcare accessibility for low-income patients. With Predicare, a small subset of this patient population will receive huge benefits. Thank you for your time.
Go ahead, guys.
Good morning, everyone. We're Team Soul Drone. I'm Trisha. This is Tage, Daniel, and Dominic, and we're building a mobile drone charging solution. So the inspiration for our project really came from looking at disaster relief and the way it's handled today. Looking at this picture, it's very clear that areas affected by natural disasters are very hard to navigate through, and indeed can be dangerous for first responders to do so. Certain organizations, disaster relief organizations like the Red Cross, have begun to turn to drones to address this problem. But using drones has its own set of issues. Drones expend huge amounts of energy when flying, which limits the amount of time they can be in the air, how far they can fly away from their charging stations, and 3, requires them to carry huge batteries. These problems greatly limit the scope to which drones can be used in disaster relief. For example, the Red Cross is trying to combat these problems by using drones that are tethered to their power supplies. However, this introduces its own set of problems because now these drones can't actually have any range. They can only fly up in the air. So this brings us to the question that our group decided to ask, which is, how do we extend the effective range of drones? Our solution was not to bring the drone to the power supply as the Red Cross did, but rather to bring the power supply to the drone. We did this by creating a solar charger that we attached to a large carrier drone, which is then mobile enough to go into the fields to charge other smaller mini drones. Our objectives when creating our design were to, 1, create a solar charger that was lightweight enough and so that it could be carried by a drone. 2, capable of providing 5 volts USB supply to charge our mini drones, and 3, created such that mini drones can charge upon landing on a charging pad. After considering our goals and our objectives, we decided on our current design. Our current design consists of 3 main parts. As I mentioned earlier, our lightweight solar panel, which we decided to make foldable, will sit atop our large carrier drone, which will also hold landing pads that extend from the main body of our drone. Our vision is that upon landing, our carrier drone will be able to unfold its solar panel. After doing so, charging circuitry on board will regulate a 5-volt USB supply to landing pads that extend from the body of our drone. Our mini drones, which you can nickname parakeets, will be able to land on these landing pads and charge. So now that I've given you a broad overview of our system design, I'm going to pass off to Tage, who will give you some more details.
So, firstly, for the charger design of the drones that we're using, we use the DJI F450, the flame wheel. Mainly it's lightweight, has a good payload capacity, and it's not too expensive for what it's able to do. And we use the Parrot Mambo Fly. It's the smallest Parrot model, so we nicknamed it the Parakeet. It has an 8-minute flight time, and we chose it because it has recon capabilities. It has a camera on the bottom of it. It's very easily programmable, and it's relatively inexpensive. So for the charger design, for the large panel, we use something called the Miurafold. The Miurafold is important because it only requires 2 points of actuation to pull and push in order for the whole thing to fold out. It's also important because most solar cells that are commercially available are square, and so it makes it difficult to do any more complex designs. So these can just be sandwiched inside frames, and then a fold can be made. So we have 9 3.4 watt SunPower C60 cells. They're lightweight, they're very, very powerful, but in exchange for that, they're very fragile. So we had to sandwich them inside acrylic plastic frames and then coat them with EVA film so that they're protected from dust and UV. And then finally, they are connected by duct tape. So you can see here, we have basically just duct tape that has the folds. Powerful rubber bands will then pull them in the right direction when it's time to compress and expand. The solar cell performs pretty well within the power requirements we need. It can do up to 30 watts in very, very optimal conditions, but we don't actually need that, especially if we want to deal with overcast skies or later in the day. We won't be seeing 30 watts, however, we don't need that much. We need probably about 3 watts, and we've been able to get that with our Parrot and just in regular conditions. Finally, the landing pads operate by folding out using these scissor arms. They are originally concealed under the drone, and then they fold out, and the smaller drones can land on them. They charge through contact, so there's 2 copper plates, copper sheets, and then the drone will land on those and will charge by connecting to those. Now that I've taken you through some of the more technical aspects, Daniel will take us through alternative designs we've considered through the semester.
Thank you, Tage. So when we began working on this project, we considered a variety of designs. So at first we considered induction wireless charging, but we found that the coils required for that were too bulky. And then we also considered alternate panel designs, and we decided against just having a flat panel because we recently acts as a sail while the drone is flying. And then we chose the Miurafold as compared to a fan configuration because it would enable us to fold it up more compactly. And then we also tried to use the nozzle flight controller, but found that it was too difficult to use. And in terms of project management, so we divide the work on this project based on each of our areas of expertise. So Trisha, as the electrical engineer, handled the panel and charging electronic design, while Tage, as the mechanical engineer, handled the mechanical design of the panel. So myself, being electrical engineer and meme submat, I handled the landing pad design, while Dominic took care of the market research, motor control system, and EVA lamination. So now I'll pass it off to Dom, who will wrap up with our budget and standards.
So as you can see, our total came out to about $1,400. This was mostly due to the drone and its various accessories that we had over the various iterations. and then our second total came out from about the solar panel and those various parts. You can see our industry standards here are some of the things we're trying to keep in mind should we try to commercialize, and various other ethical standards. And to wrap up, we've mostly met our design protocols and what we hope to achieve from the get-go. We can charge a parakeet drone, and we can do so at a rate comparable to what you might find in the advanced industry. Thank you.
Thanks. You see you there? See you there? Yep. Okay. I think. Ready?
Steve, just to use Justin used this instrument well.
Yeah, you didn't have to.
Hi everybody, we're Team 18 and Data Analytics. I'm Caroline, this is Evan, Torrin, and Sam. We're two systems engineers and two computer scientists. We're going to talk about our project and how we kind of blended those skill sets in a really interesting way. So our project's about daily fantasy sports, so I'm going to give you a little bit of background about that. Essentially in daily fantasy sports, a user picks a team of real players, and then they earn points based off the performance of those players that night. So it's on a daily basis, and thousands of users will put in rosters, and then whoever does the best will win prize money. So why do we really care about daily fantasy sports? In 2017, about 60 million people in the US and Canada participated in fantasy sports, making it a $7 billion industry. Additionally, there's a huge element of skill involved, as evidenced by the fact that the top 1% of players earn 91% of the prize money. Most people make their decisions just based off of personal knowledge, who they think is good, who their favorite players are. So we saw this as a really good industry to move in, provide a data solution, and maybe make some money. So essentially our goal, provide our users with a data-backed recommendation for daily fantasy sports contests through an easy-to-use website.
The core idea behind our model is to build a portfolio of rosters. Within the portfolio, each roster maximizes both projected points and variance, and we minimize covariance across rosters in the whole portfolio. This means that while some rosters will perform poorly, some rosters will perform very well, and given the top-heavy payout structure, the rosters that perform very well will easily pay back the rosters that perform poorly. As you can see in the top left, our objective function maximizes expected points plus variance. Constraints 1 through 5 show that we follow all DraftKings rules for budget, roster size, and positions. The sixth constraint helps us make sure that we don't have overlap between rosters. We built our initial model in GAMS, which is a modeling language common in academic settings. In order to make this commercially viable and put it on the web, we moved our model over to Python and used all open source packages to solve it. After building the model in Python and solving on static data, we set out to build a website which could pull live data and display our results to users.
So in order to make this theoretical model commercially viable, we had to make several design choices. Here's a basic overview of our entire system. On the right, we have the users inputting custom parameters such as league scoring rules or individual fan preferences. In the middle, we have our optimization model, which is wrapped in a web application that allows the user to interact with the model. On the left, we're utilizing a couple of data sources where we're pulling things like individual player projections, as well as the available contests on any given day. So in terms of our application interface, we decided to go with a single-page application architecture. What that means is basically the application behaves more like a native iPhone app than, say, a traditional web page built off links between static HTML files. In addition, we implemented a user accounts feature, which provides a future monetization pathway where we can charge users to get accounts. Of course, in this day and age, concerns over data privacy are more prevalent than ever. To address that, we implemented many of the current best practices regarding web application security. Finally, as Sam mentioned, our source code is all written in Python, and we're using Flask as our application container. So in building out this project, we encountered several standards, laws, and ethical considerations that were important for us to take into account. There's an IEEE standard that protects consumers against algorithms that could accumulate bias and possibly use that bias to discriminate against users. That standard is not currently relevant to our project as we don't collect any user data, but it could become increasingly relevant as we continue to explore building out a customer base. Legally, although online betting has faced controversy in the past, recent federal legislation has established online sports betting in particular as a game of skill and thus a legal entity. Finally, there are ethical considerations involved in any application that claims to provide recommendations for monetary decisions. It's extremely important that our users understand where those recommendations are coming from, as well as the extent of their predictability. This will become increasingly important as we move towards monetization and start charging users to use our service.
So now I'd like to switch gears and talk about testing and validation of our model. In our primary testing phase, we back-tested against 20 days of historical data released by DraftKings on Kaggle, which is a popular data analytics website. Over 15 contests, we placed 6 lineups above the 99th percentile, which is roughly 2 times better than the average user. We also got feedback from our early users to improve the user interface, and unit tested all website functionality. In our secondary testing phase, we entered real DraftKings contests to evaluate our returns. Here's a screenshot of our top performing lineups from yesterday's contest. So far, we've entered 40 lineups and doubled our initial investment. As our project is primarily software-based, our budget is fairly minimal, coming out to about $300. Now, we'd like to show you a live demo of the website. So in the interest of time, I'll jump right over to the generator. This is the team generator, where you can select settings like the number of rosters you'd like to generate, pick 5, and teams you'd like to exclude from the optimization. So here's your output. It's every lineup in the optimization, the projected points for every player, and their salary. And as you can see at the bottom here, the model took 3.1 seconds.
So, although senior design is coming to a close, we're actually very interested in continuing to work on this project and have a twofold vision for how we'd like to proceed. On one hand, we want to continue to build out the model. This involves improving integration with other daily fantasy sites and contests, as well as adapting the model to work with new sports. In addition, as we mentioned, we're looking to take more steps towards monetization. Fortunately, this is pretty straightforward and very feasible. Low fixed costs allow us to maintain a low level of risk while increasing potential for very profitable growth. In addition, in this market, there's actually very little competition, and industry growth projections for online sports betting as a whole over the next couple of years are very attractive. So, in conclusion, we'd like to thank a couple of people who helped us throughout this entire project. Firstly, the ESE senior design staff were very helpful throughout the entire thing. Additionally, we'd like to thank our advisors, Peter and Monique, for helping us with a lot of the domain-specific knowledge that was required for us to get this project started. So thank you very much to them, and thank you for listening.
This should be our last team for lunch.
commuters living in Philadelphia, 1 driver and 1 biker. One morning, on the way to work, they have an accident. After the accident, the driver takes his car to service and calls an Uber to go to work. The biker spends the next 2 months in the hospital. Hello, ladies and gentlemen. We're Safer Section, and we're going to show you how Safer Section is making the roads safer for us, for bikers, and for pedestrians. My name is Moni Arslan, and I'm here today with my team, Rachel Warren, Caitlin Ricky, and Olivia Warren. And we're going to show you how, with the help of our advisor, Dr. Megan Larson, we're making this possible. Unfortunately, the intersection design process is very old and is mainly geared towards cars and traffic. They're aimed to maximize traffic throughput. However, city planners choose from existing intersection designs and aim to maximize traffic throughput in those streets. However, there isn't a way to make our streets safer for bikers and pedestrians. An accepted, quantifiable safety metric doesn't exist because it hasn't been developed yet. At Safer Section, we're solving this with a data-driven methodology we've developed. This methodology can be used to evaluate and improve the safety of any urban intersection. Before we dive deeper into the methodology, I want to give you a brief overview of the process using this flowchart. First, we had our subjects take a specific route in Walnut and Chestnut Street in University City and collected eye gaze data using Tobii eye tracking glasses. Then, we analyzed this data using multiple software programs to develop safety metrics and safety interventions. Then, we modeled their implications on traffic using a traffic simulation software called VISM, and eventually combined all our findings to come up with concrete design recommendation to improve the safety of an intersection here in University City. So now that I told you about what we're set out to do, I'm going to pass it off to Rachel, who's going to tell you more about data collection and processing.
Thanks, Moni. As Moni mentioned, the technology that we use to capture this data are the Tobii Pro Glasses 2. Although these glasses have been used previously in lab-based driving simulations, we are the first team to use them to capture real-world pedestrian and cyclist data. In order to capture robust and accurate data, the glasses are equipped with 2 cameras for each eye. The gaze data is then processed through an algorithm and superimposed on a video for the user's child. Since our data collection process is fairly new, we were faced with some immediate limitations. A main limitation was with the gaze data percentage, which is affected by the weather and the calibration. However, we were still able to capture robust qualitative and quantitative data. For our qualitative analysis, we generated heat maps and gaze plots in the Tobii software. An example here shows a larger variation in the gaze peripheral data with a more concentrated focus area for bikers on an unprotected lane versus a protected lane. This indicates that the biker has a higher stress level on the unprotected lane. To further our analysis, we also studied the data quantitatively for both bikers and pedestrians. The plot on the left is a moving average plot of pupil diameter for a biker, which is used as a proxy for stress levels. We found spikes in pupil diameter at 34th and Chestnut. For our pedestrians, a gaze velocity plot is shown on the right for one of our users as they cross through 4 of the intersections in our study. In support of our pupil diameter data, we found that the 34th and Chestnut intersection has the maximum amount of gaze velocity peaks, further indicating that this is an intersection with the highest level of stress for both bikers and pedestrians. Through our analysis, we were able to determine that 34th and Chestnut is the least safe intersection. Since there is no other data-driven research in this field, we decided to compare 34th and Chestnut to the other intersections in our study to see what makes them more safe. We found 3 stark differences. First, 34th and Chestnut is composed of 3 different types of interconnected streets, whereas the other intersections in our study are only composed of 2. Next, the traffic on 34th is one way, but the traffic on 36 is 2 ways. And lastly, the 2 lanes that go into the 34th and Chestnut intersections changes over to 3 lanes when you pass through the intersection. However, for all of the other intersections in our study, the number of lanes remains constant. After analyzing these differences, we decided that in order to make 34th and Chestnut more safe, we would have to reduce the confusion and the speed at which vehicles pass through this intersection. Kayla will now talk about how we actually implemented these safety changes.
Thank you, Rachel. Using the VISM software, we first modeled the entire University City network from 45th to 33rd Street on Walnut and Chestnut. We then altered the specific 34th and Chestnut Street intersection by implementing some of those changes that Rachel just mentioned, and then viewing how that impacted the traffic of the entire network. 2 of our models are shown here, with the main change being the removal of that 3rd lane on the right as you exit the intersection. Our other models mimic this, but we've added areas for reduced speed on the approach and other smaller safety interventions. So although VISM is the leading software for this field, there were still some limitations both through this and city standards that prevented us from implementing all of the safety interventions we identified. So first, the City of Philadelphia classifies roads based on volume and neighborhood location, so we can't just make arbitrary changes to how popular a certain area is. So we had to stick to this. Second, VISM isn't really a dynamic software. It's still being developed as the field is fairly new. It requires comprehensive route probability distributions, traffic light cycle times, and a lot of other data from the city to be inputted over the entire network. Making some of these intersection-specific changes, like making a one-way bidirectional, for example, requires altering that network-wide data, which just isn't really feasible for a project of this size. So after making those safety intervention changes in the models, we viewed their impact on 4 key traffic throughput metrics that are listed here. The results were pretty significant. Even for the maximum number of safety interventions of Model 4, the traffic impact was very minimal. So this means, contrary to popular intuition, the effect of our safety metrics on traffic is pretty negligible, meaning that trade-off overall is pretty small. So due to this small trade-off, of course, we decided Model 4 to be the most optimal solution on balancing the trade-off between safety and traffic. And that's by implementing those changes that Rachel mentioned and that are listed here again. So as a reminder, the simulations and the deliverables of the recommendations for the specific intersection are only one example of how our holistic methodology can really be applied to any intersection in most urban areas to really improve the lives of pedestrians and bikers. So now I'm going to turn it over to Liv, who's going to talk about how we accomplish this and our vision of the future for the field.
Thanks, Kayla. Overall, we all contributed to every aspect of this project, but each team member took lead on a specific workflow. As for our budget, Megan Ryerson was able to secure a grant from the City of Philadelphia to cover the cost of the Toby hardware and software. As from VISM, we were able to use a university license. Through each phase of our project, there were certain standards that we had to abide to. However, these standards didn't affect our overall methodology or implementation. As research and software development continues to improve, we envision a user interface that city planners can use. In this user interface, city planners could go in and make changes in a certain intersection and see the impact on traffic throughput and the safety metric. This past semester, we developed trying to build this out on our own. Oh, I'm sorry. Yeah, we developed trying to build this out on our own. However, there were 2 major flaws with this which made it impossible for this semester. First off, the VISM API is not compatible with an external UI, meaning we couldn't build a real-time model. Second, we only had data collected for the City of Philadelphia, so we couldn't build a universal model. We suggest, in order for research to continue developing in this field, that universities and city planners use our developed methodology to explore this safety metric and also see how they can make safety changes without compromising traffic throughput. Thank you guys so much for listening, and we look forward to you coming to our demo later so we can answer questions.
Yeah, you should have come in.
You're done? The lunch is being set up. Give us a couple of minutes. Professor Andre DeHunt will take over. If you need some, think you can get to. That was the last. Oh, can you just stop? Yeah.
Yeah, I'm gonna be right back.